instead of the new one. So, did you get a new email? I just sent it out about a few seconds ago. So the thing is, it's called Python_faster, and I just mixed it up, faster Python, and this was a wrong link, and I didn't see this, and I copied it. So the file is called Python_faster zip. If you try this, maybe this works. It's working. So if you switch this around, so the words Python and faster, then you should get the download. So. Good morning, everybody. This is the second tutorial day of PyCon 2016. A very nice Portland here. Yeah, we're going to start. We have 3 hours to cover quite a bit of topics. So I sent everybody, I sent you an email in the morning with this system. So you have a few things to download and a few things to install. You don't need to install things quite yet. So if you install them maybe after doing the first half an hour or so, that should be fine if you haven't installed them yet. It's not that much. Everything should be pip installable, what we have here. So just download it. And if your download doesn't work, switch around the words Python and faster in the email. I sent new emails out right now. The problem is with the system, I have to click each and every single user. That takes a while to send email. I can't just say send email to everybody. I have to every time go to the thing and select users. This tutorial is only 20 people. The other one is more than 80, so that's even more work to do. Okay. The topic of the tutorial is faster Python programs. Don't measure, don't guess. So we talk about a few steps how to move writing faster Python programs. First, a few words about myself. So I've been using Python since 1999. So it was version 1.52 when I started. Still remember, it was in April 1999 when I bought my first Python book. And ever since I've been using Python, and I haven't found anything better yet. So I'm still really enthusiastic about it. And then I got into Python training. That's what I do most of the time. So I've been training Python since 2004. And therefore, I found what's called Python Academy, which is my company. But my main occupation lately, so I'm doing Python training. And also, I'm involved in community, so I chaired a bunch of conferences. So EuroSciPy, which I kind of pushed the first 2 EuroSciPy, 2008 and 2009. I was a chair and the main organizer. And also was a chair of 2 PyCon DEs, German PyCons, and the EuroPython 2014. And I'm also involved in the Python German Software Foundation kind of organization, so all kind of things. I'm involved there. Good. I just would like to learn a few things about you. So maybe you can raise your hand. Who's using Python 1 year and less? Okay, a few people. 2 years and less, and more than 1 year? Between 1 and 2 years? Okay. Between 2 and 5? And more than 5? Just a third? Okay, so I get just a little bit a feeling that's a kind of mix. Just the length of using language is not really a good measure, but it's some measure. So who of you is mainly using Python 2 and very rarely Python 3? About a good half. And the other way around, who's mainly using Python 3 and none? Just a few people. So I try to make the tutorial mainly with Python 3. I'll still mention Python 2. The differences are typically not that bad, not that big actually. But I would like to show the new way with Python 3, which would be more useful in the future anyways, because Python 2 is going to phased out in 3 years and something. Yeah, in April 2020 or so. That's a date now. Python 2, it's not going to be supported anymore, though sooner or later you have to switch to Python 3 anyway. So who of you is doing, or in terms of performance, doing mainly number crunching, so doing computational things? Yeah, about a third. There might be an overlap. Who's mainly doing like CPU bound? Who's very interested in CPU bound problems? So it's something you want to use the CPU? Nobody? I think number crunching is CPU bound, isn't it? Okay. Who is rather interested in memory usage, memory bound usage? A few people. So we have something memory. And who's more on I/O bound? few per IO bound. So this would be. So there's different problems in terms of performance, and I will cover some of them. Not everything. It's a big field, but I will cover all of the topics a little bit. Okay, so if you have this download, there's if download, you have this handout, which is a 75-page PDF handout here. That looks like this. So you should have this. So if you have this download, then you should go and unzip this file, and then you should find this thing here. This is a PDF with about 75 pages, and typically I print it out, but since it's a big crowd and it was finished pretty late, so I don't have it printed out, but it should be pretty comprehensive. So this is the thing I'm going through, and I have a paper version actually here. Which I'm going to use as my guideline. And we go through this thing, and we look at a few things in this material. So I'm going to use IPython Notebook. Who of you is familiar with IPython Notebook? A few people. So you don't necessarily have to do this. It's just my tool to show you. If you're more familiar with some editor or some other interactive system, IDE, whatever, you're welcome to use whatever you like. It's just using IPython Notebook is pretty useful for me because I can show you a few things directly in a notebook. And then it's a teaching tool I'm using all the time. So therefore, I'm going to do this. So I'm typically open one of these notebooks, and then we work from the notebook. So this is the download. I created a new directory, and I have my download. This is the download, and hit the download. You have this Python_fast. So that's the name of the PDF, yeah, and also the name of the zip file. And then you have a few directories with examples we're going to look later on. And what I'm doing here, I go into Python 3.5, and I activate a new window, and I'm going to open a new Jupyter notebook. So we spent some time in the Jupyter notebook. So if you know how to run a notebook, if you have it installed, either Jupyter or IPython notebook, both of those should be aliases. So this IPython project just lately changed the name from IPython to Jupyter, and Jupyter is a new name, so you can say Jupyter Notebook, but IPython Notebook should still work. So if you have older version installed, Jupyter might not work yet. You have to type IPython, and then you get a new notebook here. And I just make a new notebook. So you get this dashboard, and I make a new notebook, and I make first I rename this thing. So this is my notebook I'm going to work in, and I will do a few things in the notebook. Do all of you have the download? Who doesn't have the download yet? So I sent out an email in the morning, but I messed up the download link, so I give you the download link. This is a download link. So if you go there, so Python is going to download PyCon 2000. This is a download link, Python fast, so that's a thing. So maybe I just break this. So even it's not a valid link anymore, but you know, it has to be one line. Is this big enough in the back? Can you read everything? Yeah, so this would be the link. And then you have this download, and you have all the material for this tutorial. Good. I will talk a little bit in the beginning before we start. Okay, so the tutorial will be mainly hands-on, so you're welcome to work along. So I try not to be too fast, so you have some chance to do something. Because it's a tutorial, not a presentation per se, so I hope you have some chance to work along a little bit. As I said, I'm using the IPython notebook, or Jupyter notebook, whatever you want to call it. It's fine, you can use any kind of standard editor if you like. So you have the PDF handout, the download, obviously, and then there will be some exercises sometime in between. I give you some time to do something. And during the exercises, I will walk around and maybe help you a little bit. So we don't do too much, like we're only 3 hours and quite a bit topic, so it's not very long. And 10 o'clock we have a 20 minutes break, so you can get something to drink and something to eat. And also, they asked me that you give feedback, and this is the link in SurveyMonkey. So if you have the guidebook app, then this link will be in the guidebook app. It's not on the website, as far as I know. But if you have this guidebook application, it's there. Otherwise, I also have it in the download. It's in there's a small text file called download link somewhere, so you can click on it, not download link, survey link, so you can do this later on. Good. So, how fast is fast enough? So talking about fast Python is pretty common nowadays. So Python is a very high-level language, which is very nice because you're very fast in terms of development. So compared to many other languages, you write way less lines of code, fewer lines of code, and you're much faster prototyping something. This has some consequences, so it can be slow for some types of computations. It's not slow for everything per se, so saying Python is slow as a general thing, it's not right. It is slow for certain types of things, especially numerical computations, stuff like this. Being slow might be a problem, might not be a problem. That's maybe the main concern. You have to identify the problem and you have to quantify the problem. That's what this tutorial is mainly about. That's the most important thing. You have to identify and see what is my problem and put the problem in numbers and have something. Then you start solving a problem to measure how you improve. So very often when you optimize something, it can come at a cost. So I'll try to show you a few approaches where you improve your code and at the same time make it faster. That's a nice way to do it. But sometimes if you want to make it faster, you have to make your code harder to read, make your code longer, use some other constructs. And this is twofold because when you do this, you have to invest more in writing your code, and also, maybe more important, you have to invest more in maintaining your code. So you have to weigh the costs for the benefits. So that's something I hope you will see here in the tutorial. And you might have more work to do. And you need to balance both of these requirements. So you might know this very famous saying, premature optimization is the root of all evil. It's not really clear who actually said it, but it doesn't really matter. It's a pretty good basic principle to work with. So don't bother about optimization in the first place. Just get it working right first. So pretty much optimization, you would write everything in assembler in the first place, so make it fast, which will take a very long time. Obviously, nobody's doing this anymore. And I hope I get this across a little bit. Okay. One of the things when you start doing optimization, you have to make sure that your program works correctly. For this one, you should have some tests in place. And it's really important to have some program that's really doing what you want. Because optimization and developing at the same time, it's not a good idea. So make it work right before you make it work fast. So, as I said, it comes as a price. It tends to make your code less readable. It's not necessarily always the case. Depends on the approach you're using, but this is often. And very often the readability can suffer if you do so things. So if you have to add stuff here, add stuff there, do something different. Therefore, you might reconsider what you're doing. It's not always possible to get it readable and fast, because sometimes you need to write a C extension or something like this, and then it's getting much more complicated because you add more moving parts to your system. So So make sure your program is really too slow. This is the first thing. It's a kind of a strange statement, but sometimes you might not have a performance problem. It might not be Python that is slow, there might be other things. So if you work with a network, there might be the network. So what we're doing, we spend quite a bit of time on profiling here. So if you work with a network, then network might be the slow part, and you can improve your Python as much as you want. It doesn't help, the network doesn't get faster. And if it doesn't matter if your program is slow. So if it runs overnight, it doesn't matter if it runs 1 hour or 3 hours. It doesn't matter if it's finished in the morning, it is not a big problem. Those kind of things you need to consider. And you might even reconsider when you do something and conditions change if these assumptions you have are still okay. Sounds like it's common sense. A lot of things are common sense, but you still need to have this in mind. Don't optimize as you go, very important. You should not say, okay, this is probably faster, so I write an extra 3 or 4 lines to make it faster. If it's shorter and more concise and more Pythonic, and they think it's faster, that seems okay. But if you just say, okay, I add more code because I think it's faster and I will need it, you might not need this. So this is something you need to actually measure and test and have some numbers in it. If you need it, don't just assume and optimize it and you go. Very important, use your realistic use cases. So you have to really know what your program is good for. How many people are going to use it? How often is it used? Is it used only once and then never used again? It's just a throwaway thing. You might not spend too much time on optimizing. Yeah. Those kind of things you have to keep in mind. Maybe you have some other criteria here. So search for some external sources. As I said, a network can be it. Databases, call the system functions. So this is something that will come out as we do profiling. We'll see where time is actually spent and what your system is doing. Architecture, so the architecture is something like a bigger scale algorithm if you want to, so how your whole thing fits together. And there might be something in architecture, and though micro-optimization here and there might not really help to get things faster, so you have to look at architecture. Okay. I mean, often you also check for bugs. Maybe you have bugs, maybe it's not a problem in your program per se, but something is wrong. Just like if you forget to print in the inner loop or something, might slow you down. Or some real bugs that you do something much more often than you actually need to, or something like this. So now, once you have the case, so for the rest of the tutorial, assume we have a case, otherwise it would make sense to do it. You have to actually do profiling. So I have spent quite a bit of time on profiling, which I think is very essential. You need to do profiling, and then I give you a few hints what you can do. I used to have a second part of the tutorial where we actually do some extended VC and some other kind of things. It just gives you some hints what you can do. But I think profiling is the first step and the most important step because it's a basic for everything. Of course, when you profile, you need to check. So the best is you have some tests. So of course, when you profile, you might, when you optimize, you might change the result of your computations. And this is something you needed to really check for. So the first thing, and this is typically where I can gain the most, you change the algorithm. So this is something where I can get typically, if you have a bad algorithm, change to a good algorithm, get orders of magnitude of speed out of it. This is something that's really useful to think through, and we're talking about a factor of 1,000 or more faster programs depending what algorithms you use. All the other measures, like extensions with C or so, might give you 1 to up to 2, but not more typically orders of magnitude. So if you go to a GPU or something, you might get even more out of it, but this would be a bigger step. You don't cover GPUs or anything like this here. So the algorithm is the first thing to think about, to reorganize your program, how it's written, to make it faster without doing anything more difficult, going to other systems or things like this. So one easy solution is, like, especially if you have a problem with memory or something like this, just you can buy more memory. So nowadays memory is so cheap, so it might be useful just to buy more memory or just replace your hard drive with a SSD if you haven't done something like this. This would be something that could help and might be cheaper in the end than if you're somewhere where simple solutions don't work, just getting a bigger computer might be a simple solution. So of course we not go in deeper on this here. Okay, that's it so far. Now we go through this. We go through this handout step by step. This was the first chapter pretty much. And now we go to the handout and we look how fast programs are. So we have different ways of running programs. So we can check how fast things are by saying from test import Python should be. This is Python. In Python 2 it should work. So I have a Python 3 notebook. And here I can run a Python 2 cell. So most of the time I work in Python 3, but from time to time I would like to run in Python 2, and therefore I have this. I can do this import, and you have this Pystone import in Python 2, which is a simple program. Actually, there should be a Pystone 2 and a Pystone 3. So let's check in the So this is everything I gave you here. And this measuring. So if you go into directory measuring, you have a Pystone 2 and a Pystone 3. So this typically it's located in the test directory, but for some reason in Python 3 it's not there anymore. But this is a benchmark, so you can use this benchmark Pystone 2 and Pystone 3, this is Python 2 and Python 3, and you can use it from the command line, and you can use it also from importing it. So if you go to the command line, and I'm in this directory, and I change into the subdirectory measuring, and then you can find this Pystone. And Pystone is one of these benchmarks. So benchmarks are always a little bit problematic because you can always write benchmarks for anything, but it's something you can get a feeling how fast Python is. So if I run Pystone 2, so I get a benchmark run for Python 2, and you see how fast this Pystone 1.1 is. You see how many Pystones per seconds you have and how many executions. If I do the same thing with PyPy, so you might have PyPy installed, but just an example, PyPy is a very fast Python implementation, and you see now this one is a bit faster. The normal Python is 75,000, and this is 680,000. So it's nearly 10 times faster if you use Pystone for this, PyPy for this example here. So you can try different versions. You can use Python 3. So if I run Python 3 and I use Python 3, then you see the differences, how fast it is. And this is a bit slower here in my case, the implementation that I have here. This is Pystone 1.2 than Python 2.7 in this case. You can also use different implementations. There should be a JSON, I think, Pystone 2.py. No, JSON is not installed here. But when you have it in, it should be, maybe the Python on that, then you will see the differences, how fast they are. So this is something that it can be pretty useful, but now you know if you can use PyPy, then very easily you might be able to improve your program without doing anything. So that's what you can do here. And I have a small helper. I have a small helper function that's actually converting Pystones. So if you look at this, if you're in this directory, this is called Pystone converter. load PyStone converter. And this is a small program here that actually it takes the seconds here and calculates to kilo PyStones, because the numbers also make it a bit easier to read if you divide them by 1,000. And when you do this, so I'm importing PyStone here, and this only works with Python 2 here because of the so I can say import Python PyStone 3. This PyStone, that should work. And of course it's this is Python 2 still, obviously, here. So I haven't updated this one. But if you make it just to print here, then it should work. Yeah. So now you have this converter. You see, when I do something, it goes through. I can convert seconds into kilo PyStones. You have this converter, so you have runtimes and kilo PyStones, how fast they are. So I just run this function here and convert seconds in the PyStones. So I run the test here, and I get the benchmark time, and I get the PyStones. That's what I just did with the command line, and I can convert this one, so you have this measurement. So that's something that might be easier to read to do something like this. Okay, this is the first benchmark. So this comes with Python. There are other benchmarks. I'm not going into these benchmarks too much. We use some small examples later on. The first thing I want to show you, this would be the first thing, benchmarks. So I will upload this notebook after the tutorial, so you will get my notebook, so if you're interested. And this one would be benchmark. The first benchmark, so we have this, and benchmark. The next one would be profiling CPU usage. That's most people are actually interested very often in CPU usage. And we look into CPU profiling. CPU profiling. And to do this, you can use different profilers, and I'm using the one that comes with Python, which is pretty good, which is called cProfile. So the program called cProfile that's built in Python, and the C indicates it's written in C. There's one called Profile, which is written in Python, but it adds a lot of overhead, and this overhead might make it difficult to get some good results. Every time you measure, you influence the system. You have to be aware of this. When you measure, you change something. It's just a question how much you change your system. It's 1%, it's typically okay. If it's 150%, it might not be okay. So typically when you measure something very fast, then you might make typically more mistakes than if it's something long. If something takes 30 seconds, it doesn't matter if you're off by a few microseconds or milliseconds. If something takes less than what you can measure, then it's kind of difficult because you need to repeat it. But then you repeat something, you write a loop, and the loop has to be measured also, and stuff like this. It gets more complicated. Therefore, you have to be aware when you measure something, you always influence your system, and sometimes if you get very suspicious results, you should consult a different method to measure. That happens to me. I get something and it looks very strange, and then I try to do it in a different way, and then if both things correspond, then it's likely that it's okay. If they're not, then you might have to search for the reason. So that can happen. So let's look at some profiling here, and I have some scripts. If you go in this directory, and then I have a few scripts that you can use. The first one is called Profile Me. So with this, in the IPython notebook, I don't have to go to the editor all the time. I can use load, and I can use Profile Me here. Profile Me and .py, and I load this one. So in this one now, it's really written for Python 2 and Python 3. So I have a very simple check. So typically, when you do more serious work with Python 2 and Python 3, I would recommend using something like Python Future org, which is a very nice system to write single source Python 2 and Python 3 code. For this simple example, you don't need it. The only thing that's different here are range and xrange. You might be familiar that xrange is a Python 2 only thing, and the new range in Python 3 is pretty much xrange plus a bit extra. So for our purposes, it's just setting range to X range if it's Python 2. Yeah? So if it's less than Python 3, I set it. So now I have two functions here. The one is fast, that waits about a thousandth of a second, and a slow one waits about a tenth of a second. So sleep, time, I import time from the standard library, and time sleep puts the processor to sleep. So this thing is a little bit problematic, especially under Windows. This time sleep can be pretty coarse. If you use a very small number, time sleep in Windows, it's totally off. So the numbers can be totally off. You have to be careful with the time sleep. But it's just an example. A thousandth of a second is still okay. So you can mimic something that takes a long time. In this case, it just puts a processor to sleep. And then you write two functions. One is called use fast. Here, this is using the fast one in a loop of 100. So I write for underscore. So I don't need this name here, so I use underscore as a kind of anonymous name. 100 times call this function. That's all. That's my whole script here, what I'm doing here. And now I'm going to profile it. And to profile it, I can import it. Well, actually, I don't need to import it. I just can execute it. So you can import it or execute it. Now they will be available. Actually, it's doing it right now. See, it's still running. When I do this, it's doing the execution because the name of my notebook is main. Yeah? You might be familiar with this name equals main thing. And this is true for my thing, and it's running it. And when you see this, now the star is gone, and you see the number, and now it's executed. Okay, what I'm doing, I have this one, and I import cProfile. So you're welcome to work along. So cProfile is this profiler that's included in Python, and it seems like we will use quite a few tools that all of them use cProfile as a basis. So we use visualization tools, which give you nicer visual output, but all of them use cProfile. cProfile is written in C, and it's a pretty good profiler. You might find another profiler, but I just focus on cProfile. If you have special needs, you might use different profilers. There are different profilers out there, but cProfile is pretty good. So, and I make an instance of this profiler. I say cProfile.profile, make an instance. And now I have several options how to use this, and the simple one would be using run call. Profiler.run call. Run call, and then I can just put in my number, my function, and I can say use fast. So here in the handout, if you look at this PDF, I say module name dot, but I load it here. I don't have to say module name. I can use a function itself. I can say use fast, and this is actually running this the profiler here. And now you can look at the output. You can look at the output. Profiler.print stats. So it prints statistics, and then you see the output, which looks like this. So it's a little bit off because I have this big. So if I make it shorter, it looks like this. Maybe it's too small. We might see it. So this is the output of this thing, and this not only works. We will see in the notebook there are some shortcuts to do this actually, but this is the output, and I make it bigger again. So you can see here the first one. The first column is the number of calls, so there's 100 calls to this function, and you see the total time and the time per call. So everything is very fast. You see a lot of them are just 0, but you see this function takes pretty much all the time here, and you can distinguish it. This is a very, very simple example. If you have a real program, this thing might be much longer. It will be much, much longer. But very often, which is a good case, you have only a few functions that take up most of the time. It is important to identify this, and cProfile gives you a way to look at this. Okay, you can do the same thing, and you can either make a new instance or use the same one. So I make a new instance here, cProfiler 2, because if you make the same instance, all the numbers will end up in there. So, and I can do the same thing, profiler 2 run call, and I run the call with this fast, use slow. Just to see the difference, use slow and profiler 2. And now I'm doing the same procedure. I print the statistics, and then you will see it's still running. Print stats. And now you see a difference. You see now the time here, it's the 10 seconds. Yeah, so of course it makes sense if I do this 1,000 seconds 100 times will be 0.1 second, more or less. If you 0.1 second 100 times will be about 10 seconds. And that's the numbers are not totally correct, but this is about 0.1 second, and this is about 10 seconds. And you see all the time is spent in sleep. That's what you expect. This is a simple example. It's a generic example. You know what the result will be. But it's a good thing to start with something simple so you can see how your measurement works. So if you maybe write your own tools a little bit, you should always have something like this. Then you can really say, okay, I know exactly what's supposed to come out, and then you see if it comes out. If not, then you have a problem in your tool. That happened to me several times that the tool is not correct, and you measure something which is not there. And that is not very nice. You spend the whole day to optimize something in a way that doesn't exist. So you always have to be a little bit questionable about those measurement things. So that's something, those tools make mistakes. And the more tools you have on top of each other, if you IDE on top of something, like if you use Spider, so Spider's an IDE, and we do timings in Spider, they're off. So a lookup in dictionary is not faster than a lookup in a big list, which is it's not right. Even here, if you work in the notebook and you use time it, default time, we're going to do later, you will see there's something that doesn't really correspond with what you want to run from the command line. There's a difference. Because somehow the system interacts, and that might happen. Okay, now we have some measurements, and now you can look at these numbers and all. This is very simple here, but now you can do something. There's a different way of running this, so you can direct say cProfile run, so a shorter version. You can say cProfile.run, and you just supply your function call as a string. So that's something you can do. So if you do this, then you get an output right away. This is pretty much the same thing. The other one I did in 2 steps. So if you want to do it programmatically, then you typically want the first one, you do some runs and you collect this output and you do something with the output. And here you can do something like this. So you can run it. You can also save the whole stuff. So if you want to save this in a file, and that's what most of the tools actually do. They use cProfile and do the profiling, and then they get an output file, in our case. So the second argument, the optional argument, would be an output file, and this output file has all the stuff in there that you can use later on to do analysis on it. And we look at some tools here that help you to do analysis, and you can do this. So later on you can load this again. You can say import pstats, and this is a helper that can read it. So if you want to, you can fortify your program with a bunch of these calls, save the results in stats, and then later on do post-mortem analysis on it. That's pretty useful. And now I can make an instance of this class pstats.stats, and I just throw in the file name, and then you have the same result. That's pretty useful. If you do this, and now I have the stats, and you can now treat it just as the same as we did with the profiler before, and we can print the. See, there's a lot more prints here. There's a lot more output. There are a lot more things you can look at. I'll just give you a few examples here. So you have this stats, and you have the same output, and you see these calls, and you have our 100 calls to this function. Now, as I said, there's many options how you, yes?
I'm sorry, I missed what fast, the second argument to run those, the fast.
Yeah, that's a file name. That's a file name, and if you look at the file system now, there's a file called faststats here, which was produced, and it's a binary file, so you don't have typically there's some Python pickling or marshalling format or something. So typically you don't look at this. Tools read it. Yeah. So that's not for human consumption. In most cases, you will read it as a tool. That's a result of the. This is important, so you can do your profiling, and you produce a bunch of these files, and then post-mortem you can analyze those files. That's typically what most of the tools do. So, and this format can be, I will show you, we will look at SnakeWiz, and SnakeWiz is doing exactly this. They read this fast stats file and give you a nice graphical representation of it. That's what you want. Yeah? Depends what you want. Sometimes you want to do something like this because you want to do, if you have hundreds of files, you don't want to look at hundreds of pictures. So it doesn't make a lot of sense. So you would write your own tools to go through, sift through, and do something with it if you wanted to. So. And you can use this pstats because pstats reads it, obviously. So now I can also sort something, stats, and then I say sort stats. And now I can say by what I want to sort it. So I can sort it by the number of calls, not class calls. Calls, and then I get something sorted back, and then I can print it. You can do other things with it, but for now it's trying just to print it. And then you see now it's sorted by the number of calls. So n calls, this 100 is the first one. Per default, I think it's by time. You see up here, it's it's by cumulative time. No? This time here, the whole thing, the outermost function takes the most time. Yeah. So if you cannot follow me, just look in the PDF. So I just go along the PDF. So you should be able to follow. That's typically what I have. Most of the time I have it printed out, so you don't have to switch back and forth. So then if you cannot follow, you can always read along and see. Because my screen is not big enough to keep everything, especially if it was printed out. So just take advantage of the thing. Everything should be typed in here, so you should be able to read it in there. Okay, so you can sort all kinds of things. So you can sort by number of calls, you can sort by time, and so on. So I take it, just copy this line, and you switch this string. So you just put the column. You just put the column name here. Yeah. So this column names calls on time. So if you put the time here, now it's sorted by time, and now see it's not the number of this is. Yeah, this corresponds because it's the longest time, but it doesn't have to. So you can sort it by all kinds of criteria. And you can also find out who is calling whom here. And then this one you can do with stats print callers. Print callers. You see, you have callers and callers, and then you find out who is calling whom. Just a question in which way you want to go fast, and then. You get this who's calling whom. You see this here, because since I'm an IPython notebook, you get this information from there, but you see who's this use fast is calling fast. Since I have to have a big zoom, everything is a bit tangled up, otherwise it's easier to read if you have it smaller. And also you can do it the other way around. You have the callies, you say print stats dot print callies, and you say use fast, and then it shows you use fast. Then it shows you the other way around. So that's very simple. So if you have, of course, if you have more complex systems, you have hundreds or thousands of functions, then you get a long output. Okay, this is standard Python. What I showed you is standard Python, and you can do it wherever you want. You can write your own programs. But the IPython notebook makes it easier. So IPython notebook, you can do exactly the same what I'm doing here, but it's easier. You don't have to do all these imports. So if you because in the IPython notebook, you can use this prun magic commands. So IPython notebook, it comes from the scientific area. And if you go to SciPy, your SciPy, pretty much everything is using IPython notebooks all the time. But nevertheless, even if you don't do scientific stuff, I always have a notebook open to try something out. So if you do web development with Django, the IPython notebook might not be that useful then for scientific thing, but nevertheless, if you want to try something out, how does it work? Just list comprehension, I don't understand, you just want to feel around. Then it's typically nicer to use the IPython notebook than going to an editor, or some IDEs you can edit a file and have an output interactively, but I think the IPython notebook has a bunch of more things. You see, I'm using some of these commands like ls. This is one of the magic commands. Actually, it's %ls. It's the same thing. And the nice thing is, if you do this, it works on Windows. So if you have to work on Windows, you can still type ls. You don't have to type dir, because it's just an alias. So some people on Windows, they use IPy notebook instead of the shell because it's more powerful than the standard Windows shell. If you use PowerShell, but PowerShell you also have to learn, it's very different than Bash or anything. So I just lately had to look at some of the commands, but if you don't know this, it's a new system. So if you can use prun, so prun is one of those magic commands. And magic commands, if you don't know what it's doing, you use push the question mark here, and it gives you a help message. So the question mark in IPy's notebook gives you a help, and the double question mark actually gives you the source code if there's any available. But pretty nice system, and see, you can use it similar to a command line tool. You say, okay, options, and then a statement. So you can run a statement. So not only an expression, a statement, you can put anything in there, and it gives you profiling, it gives you output, and it's quite a bit explanation, and takes some switches, so you can limit how often things are done and what's returned and many things. So, and now you have all those arguments, and pretty much everything I showed you right now can be done through this prun command. So I close this, it's a long help, and now I can just do the same thing. I just say use fast. I'm using the fast enough because the use slow takes so long. And now it gives you the output right away, and nicely formatted. Yeah? So that's the output. And now you can get pretty much the same thing, what you want. Also, you can limit things, for instance, some of those options. So you can say prun use fast, prun use fast, and then I give it limited to 2, and then you get only 2, limit 2. You get only 2 lines. Yeah? So if you have a lot of lines, then you might want to limit it to some certain lines. Typically, only a few lines are interesting most of the time. And this prun also has a return value. So actually, you can create this stats object, what I just did, and then you can work further on pragmatically. So many of these commands, they have a return value. So it's not like in a normal command line, you get just 0 for everything's okay and something else for something wrong. But here you get a real value for it. And you can say, okay, repeat. And you say use fast. And then it just call this. And then you have a stats object, which is returned here. So it gives you the stats, and then you have a stats object. That has all the thing we just seen before, and you can get this output from this stats object. So it's pretty interesting. So it's much more useful for a lot of things. So you can say, okay, sort by sort stats as we did before. Stats, and then you say call and print. Calls. So this one would just give you this object. You could work, but if you print, then you have some visual output. So that's exactly the same as we had before, but you just the prun is more comfort. It's much more comfort to do this. You don't have to do all these imports and stuff. You can work with it. You can also sort the output directly, and you can sort it by multiple things. So you say, okay, I want a prun, and I want to sort by calls, and I want to sort by time. So it sorts by calls first and then by time. And then you just use your function. So it's a lot of things you can do. Now we can actually call this. Of course, it has to be a statement, and now you get this output here. And this is by call first and then by time. You can also save things to a file, so there's plenty of options. So the -t. So if you do the same thing, prun -t, and then you have the file name. It's a text file. This one's called like this, and you just say use fast. And then you have this, get the output, but you also still get it into this file, and I can look at the file. Of course, there's a less command here, which is nice, and then you can look at this file. Stats.txt, and then you get the same output saved there. So those kind of things are there. And you can also use a stats file, so not the T option. So the T option would be a text file with human readable output, and if you use a D option, then you get a stats file from ipython.stats, and then you get this stats file that you can, it's a capitalized D, and then you have this output in the stats file, and then you have, so if you look at this, yeah, see, it's now there, the file exists, and then you have this. You can look inside. Okay, that's very nice. So you're very quick, you can play around, and you get some information of what's going on, and you're working with it. So I see a lot of Macs. Who of you has to work on Windows from time to time? Nobody. You're lucky. So sometimes you need to work with Windows, and the problem is the Unix systems, the Linux and Mac, it's close enough. There are some differences, are close enough, because they are kind of Unix-side kind of systems. But if you work with Windows, then you have to be aware of this differences between this time measurement function you use actually to do timing. Okay, so let me have a look at one of these files. Then you look at this, I don't know, I didn't put a name here. Which file is clock check? So, clock check. So, this is a small helper function here, which again works with Python 2 and Python 3 alike. And here, there's two different timing functions in the timing module. One is called clock, and one is called time. The thing is, if you use time, this time is okay on Windows, in Linux, but if in Windows it's very coarse, so it doesn't give you enough resolution for most purposes, and therefore you want to use clock, but clock has a different meaning in Linux. Linux means it's the CPU time since you start your process, so it's not the wall clock time, so you have to distinguish between wall clock time, so the time that actually elapses when you start something to the end. And if you use sleep inside, 10 seconds, it's 10 seconds. But the clock, the CPU time when you sleep is very small because the CPU is not doing anything, it's waiting all the time. And that's a big difference. Most of the time, very often you're interested in wall clock time because that's what you're concerned about. Therefore, when you run something on multiple processors, you might have higher CPU times than wall clock time. Because every CPU, if you have 4 CPUs, theoretically your CPU time could be close to 4 times as big as the wall clock time, if you have an ideal solution. Typically it's not the case, but you can get close to it. And that's a concept you have to understand. And that's what I have here. I have this small checker, and you can use OS times here, so this gives you a time, and then you have this clock, and you have the default timer. So the thing is, the message is, when you do time measurement, in Python 2 always use time at default timer. You can use it also in Python 3. There's a new perf time in Python 3, but it just aliases through time it. So if you need to get the timestamp, that's what I'm doing here, use default timer. So when you do this, then it's independent on the platform. If you use time, it might not really work on Windows. You never know where your script ends up in the end to doing something. So when I have this here, and I just do something 1 + 1, and I just measure the time. And if you do this, then you should see different timings here, and if you run this on different system, you might do something different. So this OS time 0 is pretty much the same thing as time clock, which is here the CPU time, and this duration here, you can take the T out, but it still works. It's a bit higher. You see, this is duration because I have this some other things going on. This is the default timer. It's about 1 second. It's about 1 second, and this OS time, the time clock, which is the CPU time, it's less than this. This is 1 second. Yeah, so I do the timestamp here. It's start timestamp. The problem is I have all 3 of them, and then I measure the duration here of how long this takes. and then there's some difference. If you run this in Windows, you will see different numbers. In Windows, this clock will be about the same time as the duration. Down here, the full timer. So this is important to know when you're in a different system, the time measurement. So this can be a big thing. You never know what systems you're going to run on. And if you have a wrong system, have the wrong time measurement function, then you might get totally different results. So you have to be aware if you're using measuring wall clock time or CPU time. That's a big thing to look at this here. And have a bit more of these. Yeah, that's to take this apart here. Good. Quick look at CPU time, then we have a break. Just have a break here. CPU time. So I have the CPU time function here. So if you want to measure CPU time instead of wall clock time, so per default, cProfile always measures wall clock time, so the time it really takes from the beginning to the end, but sometimes you might be interested in CPU time, and then you can do this. You can actually supply your own CPU time function here, and see, that's what I'm doing here. If I'm on Windows, I'm using OS times 0, which gives me the CPU time. When I'm in Unix systems, which are all others here, so I don't know if there's other systems, but then I use time clock. And then this is just my simple setup. So you see I have a function that waits for 2 seconds, and then I have this million loops here, 100 million loops. I do 100 million loops, 1 plus 1, and then I test both of these. And then I can use my profile the normal way, or I can supply my own function CPU time, which is just wrapping this. This is this function. And this, depending on the platform, is using a different function here, and this function will be called to measure this, and you will see the differences. It takes a bit here to run this, and you just see the output, and then you can, if you want to, measure CPU time instead of wall clock time. This is important, and you have to be aware what you're measuring, which one of these. So if you, the first one, you see you have this 8 seconds here, and here I have about 6 seconds. The difference, because I'm waiting, the difference is this waiting of 2 seconds. Yeah? The waiting of 2 seconds is the difference between the 6 and the 8 seconds. Because I have this sleep, and the sleep will be measured. Normally, when you use wall clock time, the sleep will be included in the measurement. If you use CPU time, sleep will not be included in the measurement, and the time is not there. So that's important. So it depends what you're interested in. So if you have to pay for CPU cycles, you might not be too much interested in wall clock time if it doesn't matter too much, then you might want to use CPU time. I don't know if it's exact, but it gives you some indication if the difference is big. So there might be something you need to check, but this might be interesting if you're more interested in CPU cycles. Okay, so 10 o'clock is break time. There's some food and some drink out there. We should be here in about 20 minutes. I would like to start in 20 minutes. I try to be here after 15 minutes, which is about, now it's 10:02, so if you're here 10:17, it's good to have not an even number, so that people will be here. So we can start 10:20 pretty much. So I don't want to lose too much. We have a lot of things to cover. So get some coffee, get some tea, get something to eat, and we meet back in 15 minutes here and continue with the next topic. Okay. Okay, so we still have a minute. Any questions so far? So we're still missing only 1, 2 people. Maybe you have a question about those kind of things. So because the next step we want to look at some visualizations how to visualize things. Okay, let's continue. So we have this basic concept how to do profiling with cProfile, and important that we distinguish between wall clock time and CPU time, which are different concepts, and unfortunately you might need to use some different functions or different platforms, otherwise you might get some results that are not really useful. Now let's look at a little bit more complex function that does a little bit more than our just sleeping here, and then it makes it more interesting to actually profile this more complex function. Not really complex, but a bit more. And this is in these files. So if you go to the directory Pi, then you have two versions for calculating Pi, and the first one is simple Pi. So this is a very simple thing. You might know this. It's a very inefficient way to calculate Pi. You know, this 3.14 something. And this is just using Monte Carlo. So we don't have to get too much into the algorithm here. It's just using Monte Carlo method, which is just doing something many times. And in this case, it's just taking advantage of some geometrical properties and essentially calculating random values x and y between 0 and 1, as the coordinates of a point. Then you check if this point is inside a circle or not. And the measurement of this one you can use to calculate Pi. So there's some mathematics behind it, but it's not too complicated. And this is just a function, but we have to do some work here. So we actually import, as you can see here, the mass module, the random module. The mass module, mathematically speaking, is not really necessary. You don't have to use the square root here, but just to have to do something. And I calculate two random values here. So I call out to external functions. That's interesting. So the random and the mass square root, and the rest is just a loop and a few calculations. So this is this function here, and typically I use it also in other courses. We have one course in June called High Performance Computing, where this is a part of it, and then we actually go on and try to improve things using different tools like Number and Cython. There's 2 days just on Cython and other tools to do this. And then this simple function calculating Pi is useful because it's also very easily to parallelize this one. Use multiprocessing with it because it's embarrassing parallel. You can chop this thing apart in many sub-functions that do just parts of it, and that works pretty well. Okay, that's what I'm doing here. I'm running this function, actually, and I get out Pi. You see, it's pretty off. So even though I use here a million, you see it's a loop of 1,000,000 elements, and it's just only 2 digits. 2 decimals are fine, and the third one is off already. So you have to use a very high number. So it's a very inefficient algorithm in this regard, but it produces something. The second one I want to look at is NumPy. So NumPy, who of you is using NumPy? So a few of you. So if you don't know that, NumPy is one of the most basic or most used modules or packages for scientific computing and works with numerical arrays. So if you do some calculations with a list of lists in Python, it gets really slow. And NumPy is mainly written in C and offers mainly an array type, so a multidimensional data type that can be used. And that's what I'm doing here. I'm using this NumPy. You see import NumPy. It has to be installed if you want to test it, but it's not essentially here. And then I just calculate random numbers, and this one is different. See here, I have to write a loop, and I have to call random 1,000,000 times, which is 1,000,000 times a function call in Python, whereas here's only one function call in Python. And behind the scene, it's doing it. So the total it's 1,000,000 here, then. It just gives you an array of 1,000,000 random numbers. So you don't write a loop. You will get faster, we'll see. The thing is you pay with memory because now you put 1,000,000 random numbers in memory there. It's a very common concept. Very often if you use more memory, you can speed up things considerably. That's what I'm doing here. So the way NumPy works here, you create a million numbers, random numbers for x and a million for y, and then another million for the distance. And then you just calculate here. And you see this one is the same thing. It just checks if the distance less than 1, and you count it. This is this just to see the difference between these two here. And now we can measure and you can see how things go. Okay, this is some complex function. We're going to have a look at it. Now I want to use a few tools to visualize this output. So we learned that you can save all this output of the cProfile in a file, and that's what you do. You save it in a file, and then you run tools on it to look at this. I used to use run snake run, which is a tool that still exists. The problem is so far it's only there for Python 2. There's no Python 3 support, and doesn't look like there will be Python 3 support anytime soon. Therefore, I would favor a different tool, which is SnakeWiz, and this was on the list of the installation. So you can use SnakeWiz to actually visualize things. So if I go to the command line, so I have my stats module here. See, I have these fast stats and these slow stats, and now I can use SnakeWiz actually to visualize this. And I think I need to activate Py3.5 because I did it with 3.5, and I can say SnakeWiz, and I can just use a file name and can do this. Maybe it's not installed here. Make another tab. Okay, it's installed here. And what it's doing now, and now the thing is, I use SnakeWiz with Python 2, but I generated with Python 3. Let's do it with Python 2. So I can use it now with Python 2. I say it's the same thing. Run the module cProfile. So I can run it from the command line actually. cProfile, and I output something, and I say okay. I've forgotten the name of the file. It's yeah, so let's do it for the Pi. It is easier. Go up and go to the Pi directory, and we do it for the Pi because it's more interesting anyway. So we say Python -m. So we run this cProfile, and I specify I want to have this the output pi.stats. I can produce this PyStats file here, and I just use SimplePy. I run it through SimplePy, and this produces a stats file. And now I can use SnakeWiz, and actually visualize the thing. And I say, okay, I want to have this pi.stats. It's the same file name I just chose, and we'll visualize it. And we should see something like this. So you should see a graph like this, and this is a visualization thing, and you have some settings here, and if you go in here, then you'll see, now it's too small, but on the left-hand side you see these different functions, and you see the functions, how they are called and what time they take. This is very interesting. This is the starting function here, and this is the next function in SimplePy. And you see how much, in the left-hand side, this is the small one. If you look at this, you'll see how much time it takes and what's going on. Yeah? So you have this is a random here, random, for instance, and this one here is a PyPlane function that's called, and this is a SimplePy directly, and this is the file. Yeah, this is a test module. This is a test function down there we called, and this is a PyPlane function, and this is a random, and this is the mass square. Then you can see very nicely where the time goes, where you use time, and you can really understand what's going on. This is the same information we just had in the table, just in different representation, but typically it's nicer because you can see at one glance where the time goes. You see, the bigger the thicker, the more time it takes. The more time it takes. Yeah. And this is just a small one. This is just here doing something going on in a random module here. That's in a random.py module, and there's something small here. Yeah, so if you go over it in the left-hand side here, then you will see what's going on, and it shows you. It's too small for you to see, but you can still see the color changes when you can over it. You can also click on something. If I double-click on here, now this one I double-clicked is the innermost. It takes 100% of the time, so to speak, where I start from. So, and this one now is a test function, and this out here is this simple. It is a PyPlane function, and this is a random, and this is a mass square root function. Yeah? And if you reset it, you go back to the original view. That's pretty nice. And down here it gives you a table. This is the same information, but in a table, and you see the number of calls to these functions and what happens. So there's a lot of calls, but most of the things just happens up here. Yeah. So that's a number of calls to the random function. This is a number of calls that go to the square root. Yeah. Twice as many because of all the 2 calls to random. That's something you can do. You can have the statistics, and you can look at this. And that's pretty interesting because you can do something with it. So the same thing, you can do the same thing for NumPy, then you will see a different thing. Now you run this one for this plain Python one, do exactly the same things for NumPy, and we use the same things for NumPy. I just can kill the server here, and instead of running this normal one, let's just say NumPy starts, and then you get this result for NumPy. And now you can run snake with a NumPy starts. And then you see a different output, and you see more complex things. See, now it's much more complex because NumPy in the background calls a lot of functions. And it gives you a nice impression what's going on, and you can go in here and you see this is, of course, the module itself, and this is what's going on. This is now it actually is measuring the import of this NumPy. This is init in NumPy, and things going on here. This is what's this? This is all these init functions. Yeah, but much more complex because NumPy is calling a lot of stuff, doing a lot of stuff in the background, and you get all these things in here, and you can look at this. So in general, it's much faster using NumPy, but you get a different output. So I'm going to actually here start a second notebook with Python 2. Okay, now you can do also quite a few things from inside the notebook. And I do a Python 2 notebook, just in case, because I have a few things. Python 2. Okay, and I just take off these things. So you can also actually install these things in the, you can load the extension, snakewiz if you have this, and then snakewiz doesn't come. Yeah, and now you can call a function and can actually visualize a function in snakewiz. So I write a very simple function, or I can import my Py. I'm a Py already. So import simple. Hi. So I can call this function here. And actually on this function call, this is very wrong. This function call now I can visualize it with SnakeWiz. So I have the SnakeWiz extension, and you see now it just opens this. Okay. I don't know why this. Obviously, you have some problems. It used to work. I don't know. Maybe change some setup, but you get the same output. So you can do it directly if it works. It opens it directly from a notebook, and I'm not sure why this is not working now. Maybe something wrong with my browser. It used to work lately. Yeah. Okay. This is one thing you can do. So you can work with this SnakeWiz, and I will always recommend SnakeWiz to look at your code because it's really, really helpful and you get a nice impression. Okay, this is the standard cProfile. cProfile works only on the level of a function, so you cannot go deeper. The only resolution you get it called by a function. If you want to go deeper, you can use line profile. So if you want to go deeper, you can use line profile, and the line profiler gives you a line-by-line breakdown of your profile. It's much slower, but you can use it because it can be really useful. So let's have a look at this profile tool. So you need to install it. I gave you install instructions. So you need to pip install line profiler, and then when you have pip installed line profiler, then you can say cProfile, and you can look at this functions. CD measuring. So I'm here now in this measuring the subdirectory, and when you have everything installed, you can say cProf, and you say v profile me .py, and this one now gives me an error. Why does it give me an error? Because this one just gives you the same output as in cProfile if you don't do anything. And for some reason, it doesn't take my argument. Does it work for you? Ah, yeah, I have it. See, but it should work from here. Ah, it works better. Okay, thank you. So obviously I messed something up with this other environment, but this seems to work. It takes a while. So if you don't do anything, this cProf just doing the same thing as cProfile. The output you see here is the same as cProfile. It's the same as cProfile. There's nothing different here. It just gives you this output. But now, if you want to, you actually can go line by line, which can be interesting. So I have a version now that's actually working with a line profiler. Let's have a look at this version. I go to my notebook here, and I make a new one. Line profiler. Because sometimes going only by the function might not be enough. You might want to look inside, especially if you have larger functions, or especially when you call quite a few of these NumPy things in one function, then you see everything in one thing, and you want to see it line by line. Therefore, we look at this file here, profile. We look at this file, profile me, and for some reason this doesn't work. Yeah, so use line profiler, and the only thing is now I have to add this decorator profile. There's no import, because now this will only run below the line profile. Because you have to put this decorator profile. This has a side effect that the code doesn't run anymore if you don't have this one. You would need to define your own decorator. It doesn't do anything if you want to keep it inside. But I made a segment version here with a profile. And all the functions that have this decorator profile will be line profile. So we see a line-by-line breakdown what happens in these functions. So this is just my two functions I had before. Now I added this profile, and it will be line-by-line profiled. And it should work. And now you can run this from the command line, and you have to give it a switch L for line profile, so it's actually doing this. And the problem is that can be pretty slow. So if I do this one, and I say L profile me use line profiler, and it takes a bit, and only these two functions that are now decorated will be broken down line by line. The thing is, it adds a lot of overhead. It makes it much, much slower. So typically you cannot do it for a whole program. You can do it for a few selected functions. But now you see you get some output for these functions, and it gives you the runtime of these two lines. So you see, less than 1% is spent actually in the range, in the loop itself, and 99% is spent calling the fast. And here it's even worse, because slow is so much slower, it's 100%. So the timing is here. Yeah, you see this timings. It's about the same for the range loop, but this time is percent much bigger, and that's why the percentage is much higher. So you get some output here line by line. So let's have a look at the function that's a bit more interesting. You can see something that's happening. So I wrote it a bit more complicated than it's necessary actually, but you see something. I have this here accumulate, and this is a very simple function that just accumulates the sums. It's like a if you know NumPy add accumulate, which is the same thing. So I adds if I have this string here 0, this list 0 and 1 is 1, and then 5. Yeah, 0 and 1 is 1, 1 and 2 is 3, 3 and so on. So it adds up. In the end, you have the sum of all these numbers. And that's what I'm doing here. So I start with an iterable, takes the first one, I go to the rest, and I have an old value, which is the last one. And I took this apart. You can do this in one line, but just to show you how much time it takes to do the steps. And I take the new value, which is the old value plus the element, and I append it to this new ACM. This is accumulated stuff. And if I do this and I run it, you should see this outcome here. Why is wrong? Yeah, so the profile, it doesn't run if I have the profile here. So if I do like this, then you should see that it's running it. But there's a profile because I run it under the line profiler. Now I run it from the command line with the line profiler. So I say minus L, and I just say accumulate. So it's the same options, accumulate, and then it takes a while. But now you see the breakdown, and you see how long it takes to do this single actions. That's why I took it apart line by line. You see how long it takes to do this assignment, how long it takes to do this loop, and how long it takes this assignment into the plus. And they're all pretty much the same time. The append takes about the same time as this one here, this loop. And that's pretty interesting. You get some feeling how long things take compared to each other. That's going line by line. That's pretty interesting. Add some overhead, and might not always be accurate. Another one, quickly, just to show you this effect. Load some calculations, calcpy, and this is just very simple. I just have a few loops here, and then I do different calculations. I add something plus 10, I multiply it by 10, I have the power of 10, I use a function power, I use a function square root, and then I use a square root here without the name. So once I use it as mass.square root, and the other time I assign square root to mass.square. This is the difference, what it takes. So if you call this again from the command line, you see this can be pretty interesting to see how long this calculations take. Calc. And then it takes a while, and you see here that this Of course, the power is a bit more expensive than a multiplication. And there's also a small difference between using this double star and using the function power. And there's a small difference using mass square root or the square root. Yeah? The access to mass square root and square root, there's a small difference. Not big, but there's a difference. Those kinds of things you can investigate here, and that can be pretty interesting. Now, the first thing, now this leads us to the first thing when you can do something to actually improve things, and this would be local references. Local ref, if you look at local ref, this is this script here. And again, I have this, you see, that's what I'm doing here. I do a try, and if this profile exists, if this profile doesn't exist, I just generate a new profile function which doesn't do anything. It just takes a function and returns a function. So if it does now, it would work. If I run it here, it should work because it just would replace the profile. But the thing is, I have two different functions. I have here the one where I make a local reference to square root and use a square root in the loop, and here I use mass square root directly. And then I run both of them and see how long it takes. So, and this would be one of those micro optimization, where I can do micro optimization here, and it takes a bit more time. And then you would see the difference in these two approaches. But that's one optimization thing. You can save this lookup. Yeah? This dot square root is always a lookup and has to look up. This one is doing it here in this case 10 million times, which takes quite a bit of time, and you can save it. If this matters or not depends what else you do. See up here, what we ever measured, it doesn't matter too much because we do other computations. If you don't do other computations, you just access it, it might be a difference that it's worthwhile to investigate, and it's still looking at it. Maybe 10 to the power of 7 is a bit too much here, but you should get an output and you see how much time it takes to do this version or the other version. Okay, now you see the difference here. Okay, you see the difference. This we don't need. This is just this is the first one. You see, if I do this here now, this takes about 50-50%. If I have this one, and here's also, it's not a big difference. It's a small difference. So it's only if you here's only like instead of 49%, it takes 52.5%. So it's not a big deal here. So it might be more useful in other places, but it gives you some indication how much you can gain when you do something like this. So it's not a lot in this case here.
In this part, you're trading a little bit small amount in this example, right? The memory to store the local reference versus the compute time that we're doing here?
I think the local reference doesn't take a lot of memory. It's just a name. So I don't think it's just one name in the dictionary. So I don't think that matters unless you have millions of these functions. But it's a local thing. It will be just allocated, and when the function is gone, it's gone. I think it's not a trade-off of memory here. Yeah, so you don't store a lot of numbers. If you use NumPy as a trade-off of memory, so NumPy typically stores everything in memory, and if you have an array with 100 million elements, you might use up all your memory, and you will get a memory error. And also, allocating memory is also time. If you have used generators and you use one at a time, and you realize after 500 of your 100 millions you can stop, then you might be faster than putting them all in memory at first and then just throwing them away. Depends what you're doing. So, but that's I think it's not a memory. It's just the lookup. So Python always looks up, this naming rule. It looks up the name in the local namespace first, and it's a dictionary lookup. If this misses, it goes to the global one, which is a module. If this doesn't work, it goes to the built-in. That means every time you call a built-in, it has to do this lookup. So you can shortcut this a little bit by just moving this built-in, or in this case, a global, inside the local namespace, and it makes it a bit faster. It's measurable, but just if it matters or not, this is a question. Yeah, it's just in this case, just a few %. And you also want to quantify. It makes it faster, but how much faster? It's a question. And if it's worthwhile to do this. Yeah. Okay, I have one more example here. Actually, it's an exercise, but I think we are a little bit short in time, so I would skip the exercise, which is unfortunate because we only have an hour and 20 minutes, and we have quite a things to cover. So I might come, if you still have time, I will do the exercise later on. And now I want to switch gears and go from profiling memory to profiling CPU to profiling memory. And there are a few tools out there to profile memory. The first one is HEPI, the Guppy framework, which so far as I know exists only for Python 2. And another one, it's the framework is called Pimpler, which is doing pretty much the same thing. There are two frameworks doing very similar things. It might be interesting to use two of them because they might give you a little bit different results. I will focus on the second one here, just because the usage is very similar and the output is similar. So I will focus on the second one. You can still have a look at the first one. So I skipped quite a few pages here. For the first one, if you look at the second one, which is called Pimpler, doing the same thing. I kept it in here just in case you want to do it. You can explore it on your own, but it's actually doing the same thing. Okay, memory usage, memory profiling. Memory profiling. Okay. Import tracker. So this works with Python 3, which is nice, and the CP, as far as I know, it's not there yet. But the usage is very, very, very similar. So memory, you will see, it's not totally accurate. So when we measure memory, you cannot typically measure small amounts of memory. It's just rather getting a big picture of what's going on with your memory. So what objects you have, what memory is used, and especially how much difference you have between different steps when you do something. That's what you want to know when you want to measure memory. And sometimes you might experience these tools not really working well, especially if you use C extensions. Yeah. But if it's pure Python, it should be fine. Okay, that's what I'm doing now. I have my memory tracker, just called M here, not too long, and I have this tracker. This Pimpler project, I think, came out of a merge of 3 different projects. One was called A size of, Heap Monitor, and Mappy. Yeah, those 3 kind of merged because they have similar goals and they merged together to this one. And this works for Python 2 and Python 3, which is nice. And I have a summary tracker. I make a summary tracker, and this typically takes a while because it's doing something. And now I can use the summary tracker and print diff, and it prints a difference. And it gives you, because the first one, there's nothing been had. It takes a while, takes a bit, and gives a diff, and gives you a nice overview of what's on your system. So you see now what objects I have in my notebook here. And you see how much memory they take. So sorted by data type. So many lists, so many strings, so many integers, and so on. And you can do something. So if you call this again, then you should get a diff. Nothing happens actually. Def should be 0 because I didn't do anything. But actually in the notebook, maybe a little bit might go on in the background anyway, but it should be essentially 0 next time. There's still a little bit left over. So when you see it's not totally accurate, there will always some. You see, this is supposed to be 0. Now here we have kilobytes, and this is just bytes. So this is more or less 0. If you call this again, then it might be even smaller. Yeah. So that's pretty much the measuring error, or what's going on in my notebook, or whatever it is. So you know it's not totally accurate to the byte. There's a few bytes sitting around here, but the table is much shorter here already, so there's not so much. Now it's less. Yeah, it's getting less and less. Every time I call diff, it will be less. That's what you can do here. And now let's have a look at a small script that actually measures the memory. Oops. And I wrote a small program which is called memory size Pimpler. There it is. Load memories memory size. And if you look inside, I import this tracker, and I'm using a dictionary to store a few things. This is a small helper, and actually I use a decorator. Are you all familiar with decorators? So the decorator is a nice Python way to introduce tools. We saw this add profile was a decorator, and the decorator can add functionality to a function without actually putting any source code in there from outside. And now you can write your own decorator. So I want to go too much into decorators, but this is a pretty useful decorator. So you have this decorator measure memory, which takes a function. And this is the one that will be applied with the add. So it takes a function, and it's doing something with your function and returns a new function that is changed a bit. That's what I'm doing here. And here, to make this decorator work nicely, use yet another decorator func2reps that makes this function here, because I changed the function. And if I wouldn't do this, the function name would change and stuff like this, and the docstring would be lost. And that's why you should do this func2reps. And then I have this function that will replace it, and I use the strange args and keyword arg syntax. You might be familiar with this. This just takes all positional or keyword arguments and doing something. And now what I'm doing here, I take my summary tracker and call it 4 times the diff, 5 times the diff, to get to 0. So I set my memory to 0. This 5 is just a arbitrary number to get close to 0. And then I call my function. So this is basic Python. This star and double star means I can get all the arguments no matter what. There can be no arguments at all. There can be all positional or keyword or any combination of them, and just hand them over. This packs the arguments and this unpacks. It just transports them over. That's it. But the thing is, I can now return the result, and I use a try finally. So a try finally means it's doing this first. So it's now doing this. It goes into here and takes this global dictionary memory and uses a function. I get this function here, uses a name. So each function has a name. And it uses a string, which is a name, and does measure diff. So I measure the diff before and after. So I set it to 0, and then I see the diff. And I see how much memory my function takes. So I see if my function leaks memory. So if my function changes outside objects, it might leak memory. This is a small helper. So you can use this helper, actually. And the thing is, if you write those helpers yourself, you can adapt them to your needs. So if you don't want them, write to a dictionary, you can write to a file if you wanted to, or do something else, write to a database, or measure something else. If you say 5 times not enough, you can change the 5 to a 10, or whatever you like. This is a complicated part. Fortunately, you don't have to bother too much with the complicated part. The easy part is using it, and using it is just, I put measured memory in front of my function, you see, and I have now this function I called make big. I get a number, and I just create a list. Yeah? So in Python 2, you don't need list, but in Python 3. So I create a list of so many numbers. So I create a list of 1 million numbers. I should run it because it takes a while. I create a list of 1 million numbers, and then since I return the list will be around after the function call, and I should see a difference in memory. And I should see that there's about 1 million integers and a list. So a list has 1 million objects and pointers. Each pointer is the same thing. Or object points to objects, and the integers are not actually in the list. They are just referenced from the list. That's how Python works. And then that's why you see the size of the list, and you see the integers themselves. And in Python 3, every integer has 28 bytes. So you can calculate, we'll see, there should be about, it takes a while, because I have to do this 5 times to get the 0, and then I get this measurements. But this can be pretty useful, because now you can use this decorator and put it there, and you see if your function kind of leaks memory. Yes. Measurement takes time, so this one makes things slower, so it will take a while. But you should see some output. And as soon as it's finished, it's still running, then I should be able to look in memory. So if I look in memory, so as soon as it's finished, we should see it. Okay, everybody understands this decorator. Yeah. So it's not difficult. So actually, it takes this function make big, which is function, and returns a new function, which I can call here, and puts this functionally. So I don't have to put this measurement in every single function. I just have to write it once and just decorate things. And you can apply it the same thing. If you don't want this decorator, you don't have to comment it out. You just have to once, as I did up here with this other decorator, define the decorator like this. So you make your measure time like this, which is just a function that doesn't do anything. It just takes a function, returns a function. Then it essentially only happens when you compile the script, and there's no extra overhead whatsoever, and nothing would happen. So you don't have to go and search for 20 places where put the decorator to comment it out. You just replace it with a Docker that doesn't do anything. That's a pretty good strategy. Yeah? And it does no overhead. When you turn it off, there's no overhead. This importing thing that doesn't. It's just one function call. There's no sizable overhead. And now it's through. And you see now here, you can see you have your million integers. Anybody knows why this is not a million, but a little bit less than a million? Yeah, that's a specific of in C Python. If you use a different Python implementation, you might see even different numbers. The numbers between -5 and 255 or 56 are reused. So you won't create new numbers. You just reuse a reference. So if you say import sys, this might be interesting. Import sys get ref count on a number like 1. You see there are 7,000 references to number 1 now. Yeah, and therefore, because this number 1 existed before, I just get a new reference. That's why it's less than a million. If my numbers wouldn't start at 1, if I would start at 500, that should be pretty much exactly a million, unless something else is going on. Yeah, so you can try. Yeah, so
Implementation specific.
that's a C Python specific. If you go to Iron Python, as far as I know, it's the numbers between -1,000 and 1,000, and have no idea of JSON or PyPy if they have anything different. But this is implementation specific because it's if you look at the get size of in Python 3, an integer has 28 bytes. In Python 2, it's 24 bytes because this unification of long and int, it changed a bit. So it's quite big. But if you just have a pointer, just a reference, it's just 8 bytes, just a normal. Yeah, so you save 3.5 times the memory if it's just references. So memory is also faster typically. Yeah. So now you see this here, and you have the class, the list. There's only one list here, and you have the size, which is also about. If you calculate, you should. It's a million times. Yeah, it's a bit more than this 8. And there's some overhead there. Yeah. But it should be about this size. It's a million. Yeah, so you can see that the difference, that's my function call. If I would have a function that doesn't return anything, just there shouldn't be any difference. There should be 0. So you can see what influence the function has. So that's a pretty good tool, so you can adapt this tool to your needs. That's always important because you just can go in the decorator and change the decorator and do something with the decorator. So I have one very similar function growth here. So it's just a variation. Yeah, this is a variation, and this one doesn't use a decorator. In this case, I have a different approach. You don't ever have to use a decorator, because a decorator, you have to go in your code and put a decorator all over the place. Here, it's a different thing. I use a function, and you can go into your modules and hand the function manually, so to speak, where can you write a script. Check memory code, so you get a function. Again, I use this args and keywords thing, and I do the same steps. So the procedure is the same. I set my memory to 0 by calling this diff 5 times, and just have the function then return it. So it's a bit different tool. Yeah, it's a bit a different tool, but you can see this. I now have 2 different ones. Here I have this. I return the numbers, and here I just append to an external data, and I can measure now the size, how much, what changes here. I use just range, and if I use range, then nothing happens actually in Python. In Python 3, because it just returns a range. But here I append to it, and yet I change this global data here. This function changes this one. Yeah, and then you see the difference here, and you can now go through. I should run it because it takes a while. I go through and put in this 2 different functions, and it will be measured. So it's a different approach. The first approach I showed you use a decorator. That means you have to go in your code and do a decorator. Here, there's no changes to your code whatsoever. That's my code down here. But in the end, I have this function that you hand in the function objects yourself, and you can do something. So it's a bit different approach to something you can do, for instance. So it will take a while. So to do the measurement, now of course, I also have to go back to 0. So one interesting thing that's really helpful is you can actually look at how Python allocates memory for lists. So you might know that an append operation at the Python list is pretty efficient. So if you append to a list, it's pretty efficient. And now you can actually visualize why it's pretty efficient, why it's so fast, what's going on here. And this is something you can do with a small script that is actually measuring the size of, I'm still doing it, measuring the size of a list, how a list grows. So maybe I need to wait a I take the other notebook in the meanwhile. Just to have a look at it. So we don't need to run it from here, so it's just to have a look at this to see how this works. And this is a Pimpler list. Yeah. And this is like this. Oh, everything works. So I have this this function. You see, I create my list here, and I have used different functions. I use this Pimpler a size of. There's a size of and a flat size. What's the difference? So one of them is actually just measuring. So if you have a list and you measure this get size of, you just measure the size of the list itself. You don't measure the size of the elements in the list. But this Pimpler offers you a function that measures all recursively everything that's inside the list. So in our other case, you would only get the size of the list, but not the size of the integers. This one would put it together and you get the size of integers. So that's a difference. So what I'm doing here, this list memory, takes the size function, either flat size or whatever you supply, and that's what I'm doing here. I just have this memory here. It's just the size function, gives it this of my list, and then I go through and just append, and then I call the size function again. So for every append, I call the size function. So incrementally, for every append, I measure how much memory is used up here. So you see how the memory grows. Pretty interesting. And then I just run this here, and down here I have this, if you have Matplotlib installed, it works. If not, you just see the output, and this is just a test. You see I have these 3 functions. I go through flat size, a size of, and this get size of, which comes, this is a standard Python module. You go through, and then it's just doing the measurement. It's just some plotting here, and then you run it, you should see some plotting. So I go to the command line to actually do this. So I say Python Pimpler list grows. That takes a while. And then you see now I have a Matplotlib, and you see that's very nice. You see this the size of the list is just 1,000, and you see the memory allocation. You see those steps, and that's how Python list works. Python pre-allocates more memory than you have space you can write in the list, and as soon as it reaches a certain limit, it gets a bigger space. And you see the steps get bigger and bigger and bigger. So even if you have if you do this append, I think 10 million times, you have about only 100 allocations, 107 or something like this. It's very efficient. Yeah? So now that's the case. Now you pay with memory for speed. You need more memory when you use Python lists. Yeah? If you use a NumPy array, use exactly the memory, besides the fact that NumPy array can store numbers much more compactly. But here, the list would grow bigger and bigger and bigger. It takes approximately, if you see here, so more or less 50% or something. There's a formula for it, but that's roughly what it is. That's the one. That's the first one. This is where I measure only the size of the list. I don't measure the size of the integers. And the next picture that should come up. Yeah, this one. Here, you see now I measure also the size of the integers, and that's why this step is not as pronounced. You see, because every time I add an integer, my memory usage goes up. That's actually what happens. Yeah? But the list itself, you have to step here. So the list members, so this is not about saving memory or anything, it's just about speed. You get much faster because allocation memory is a pretty slow action compared to CPU. And that's why if you reduce the number of allocations, then you can make things much faster. That's why append is so fast. If you say insert 0 all the time in your list, it's a totally anti-pattern because every time the list has to be copied around. If you say append, you can write in already pre-allocated space, which is very efficient. Yeah? So this is the right data structure here. Okay, and this is the sysget size of this is the same thing as flat size actually. And this is very interesting. So you learn something how lists work, and actually you can actually try it out. It's not some abstract thing somebody tells you. You can visualize yourself and can play around with it. And you can try the same thing with other structures. So you can try it with a dictionary. Let the dictionary crawl, see what happens, how much memory it uses when it changes. Yeah? Dictionaries typically don't get filled between 1/3 and 2/3, and then they get resized. You should see something similar. So if you want to, you can try it out. Instead of a list, use a dictionary. You should see the intent. And that's important. You get some understanding, you visualize something, and that really is really helpful, I think. And you can use those things to adapt it to your needs. Whatever data structures you use, you can apply the same principles to your data structures. Okay, this is stuff, and I have another script actually that's doing the same thing. And you see now this number of allocations. I run it from command line, which is the name of the script. It's a list allocations, Python list allocations. And this is now the same thing. I'm growing my list, and I do 10 appends. I do 100 appends. I do so many appends, and you see how many allocations I need. So if I start with an empty list and I add 10 appends, I have 3 allocations. If I have 100, I have 100. You see, if I have a 10 million, I have about 104. Yeah? You can do the same thing, and obviously this get size of and flat size gives you the same result, which is encouraging to at least agree here. And I think that's an interesting topic or interesting understanding. You see how things work, and then that's why lists might be faster for something when you need a dynamic data structure. Even if you work with NumPy arrays is a problem, they don't have an append. So if you do this, if you want to grow a NumPy array one at a time, you always make a copy. If you do this, you get much slower than using a list in the first place. So if you look at NumPy code, in some places they use lists internally to store NumPy arrays because it's more efficient. If everything, as soon as it gets dynamic, it might be better using lists, yeah, because you don't know how big it gets, and then later on convert it to NumPy array, for instance. Yeah? And this is the script. And let's go to our first notebook. It should have worked now. Yeah. Yeah, you see, now if I have this make big, which just returns, it doesn't change anything globally, because I don't get a reference here, just to return this one, but I don't get a reference, so it will be thrown away. There's no change in memory. And here, when I modify my global structure data, I see that's the same change in memory. Yeah, because the thing is, even if I say range, even in Python 2, but I don't get a reference. I just call this function, but I throw away the result, will be garbage collected, and that's why it won't be measured here. Yeah? Because I call this after this function call. And after the function call, that's how, if you do this in PyPy, you might see a different result, because PyPy has a different garbage collector. And if you use Python 2, you can try it out if you see something. I'm not sure I think it doesn't work with PyPy. No, I haven't tested it. Yeah, but if you would do the same thing, to do the memory, you might see a different thing because you use a different garbage collector. Yeah? So that's kind of things you might consider. Okay, just let's have a look at this script we just run. This is the one, this is allocation. You see, I have to do the steps, 10, 100, 1,000, and so on, and then I call this function, and that is the whole function here. So actually, I have this measurement function, I have different measurement functions, and I just use this function and I get the size of an integer here, the integer size, and then I have the old size of my list, and then I keep appending, and every time I keep appending, I call this size of here, and you get the size of the function there. Yeah, and then you see how many times. And this is the steps here. And if this old size and new size is greater than the int size, then you know, okay, that was a step, and I make another step. Okay, this is just a small thing that shows you how the memory is used in your program. Okay, this is, again, everything is just here done on a function level, but I can also use this memory profiler, and this memory profiler works exactly like the line profiler with a decorator profile, and it gives you a memory breakdown line by line. So let's have a look at this load use memory file. And this again is just an example. You see here, I just create the sum A, and here I use a list comprehension and convert it to a sum. Here I use a generator expression to generate expressions, and here I use a list comprehension. And then I create the sum using this in 2 lines. This is pretty much the same as what I do with A, and then I delete the squares, and I do some other computations, delete something, see how this goes and how the memory is used, and then I just let it run. And now I can go to the command line again and use this tool from the command line. So I say Python module memory profiler. I write the right contents here. And then I say use memory, and then it runs it as a memory profiler, and it gives you a breakdown. Unfortunately, this memory profile line by line, as far as I know, gives results that are not really conclusive. So it doesn't really work. This is maybe an example of a tool that's producing numbers that cannot really be trusted, I think. So if you look at this, sometimes it doesn't make too much sense. Just doing a little bit. So again, this slows things down by orders of magnitude and takes much, much longer here. Yeah, so you need to have some patience with these things. Do you have any questions about memory profiling? Yeah. So as you see, you use a library here, but you can also use your own tooling, which can be useful because more flexible, writing your own decorator, writing your own function to help you, because if you need to do something else, you can adapt it to your needs. Yeah, so let's let it run here for a while, so maybe do something else in the meantime, because this is a kind of a little bit slow action here, because it waits for a while. Good. About an hour. Okay, this is a profiling part, measuring a few things. Now actually I want to go in a few of those methods where you can actually make things a bit faster, and I'll just show you some small things. So we don't go into writing extensions or anything like this, because this would be way too much for this tutorial, and I'd rather have something you can actually apply than just going over. At the end I have an overview of all the tools you can use, but if you really want to use all of them, you can have a week-long course for this stuff. Yeah, so depends what you want to do. You have to find the right tool. That's maybe the most problem thing. Find the right tool with the right amount of effort you have to put in to put it to use. So if you use NumPy anyway all the time, there's no question, just use NumPy. But if you never used NumPy before, just for a small thing using it, yeah, you would need a few takes to get into it, probably, because you have to learn how this works and how things are. Okay, the next one is algorithms and anti-patterns. So when you want to speed up something, typically the thing where you can get the most speed out of is using a different algorithm. We saw this with our list. If you use a list and append to a list, that's a very efficient one. If you do something else, if you don't append to a list, you insert at the beginning, which is anti-pattern. You see here, now we have this measurement, and it looks not too bad, actually. So this is a memory, and then this is the increment, which is negative. So it's doing something. It allocates 32 megabytes here, because I do this list comprehension, which actually generates a list. This generate expression doesn't generate anything, but you get freeze some memory, obviously not everything at once. We freeze some memory from before. And then here this generate expression doesn't do any memory, doesn't use up any memory, because it just goes one by one. In the end, you only have one number, which doesn't take any extra space, so it's not measurable here. Yeah? But here, if you do this generate expression again, it takes much less memory. Yeah, that's not really clear. When you delete something, it frees some memory. That's fine. Delete something, it frees memory. And if you do this, multiply this string by 1,000,000. So I multiply the string A by an integer. So I don't write it like 6 zeros, so that's why I use int 1e6 here. And then you gain about a megabyte here, and then you return something, does no changes. So it gives you some indication this is not too bad. Sometimes there can be a bit off. You have to be careful what's going on here. Yeah, so that's a little bit strange, because if you cannot really trust the results, it's difficult to interpret it, if it's just the artifact of your tool or something that comes out of it. Good. This is memory measurements. So if you use this heap thing, it's very similar. So I have scripts in here that do the similar thing using heap. Or from the Guppy project. Which one is better? If you use both and compare and they have the same results, they should be fine. If they have different results, you have to investigate. So it's always good to have a second opinion. So I skipped it here because it would take too much time, but the principle is the same. Apply it, use one of the scripts, compare, same results. It gives you some reinforcement that the things might be right. Different results, you need to investigate. It doesn't tell you which one is wrong or right. Okay, next thing. So I have, still sitting here. How many have you can still use notebook. The next thing would be algorithms and anti-patterns. Anti-patterns. Let me write it. So, if I show you a few things, what you should do, what you should not do. You might be familiar with the string concatenation thing in Python, which is actually not too bad anymore, but still, you might not want to do this. So if you have a string, so if you have a string as and strings are immutable, so you cannot change a string. You cannot change a string, so it's impossible. So every time you do something, you cannot change this, you cannot modify it. So if you want to create a long string, let's say you want to create a long string, my result string, you want to create a long string, then you could do something like this: 4x in range r plus equal s, something like this. And now you get up a string r, which is 10 times. It's a stupid example, but just that you need to concatenate this one. This means actually that every time it goes through the loop, you have to create a new string. Fortunately, in CPython, this special case is optimized, so you won't see a big difference. But if you use a different Python implementation, if you use PyPy, you try this PyPy, this is a big anti-pattern. Not for 10, but if you have 10,000 or 100,000 in the loop, it will take very, very, very long. Because every time you have to allocate memory, and create a new string. Therefore, the typical way to do this, actually, you don't use a string, you use a list, you collect strings in a list, and that's recommended to do. You have a list, you have the same loop, but you start with a list and you just say an empty list, and then you say append. So here you say list append, and you just append your s. So once you're finished, you have a list with all this, and then you just do the join, and this would be the way to do it. And the join is just one operation. It knows how big the list is, and you can allocate the memory once. You have to put a dot there, and then you can put it together. This is a small thing, and as long as you work in CPython, you wouldn't feel it. Most of the time, this is optimized for literal strings. This goes away, and you won't see a difference, actually. If you use other implementations, you might see a difference. That's a small thing that might have a big impact. The problem is if you only test your program with small strings, you won't see it. You only see it if it's because the overhead developing is so big that you don't see a difference. It's only when your string gets big enough, and then it can really be expensive. So if you try this and run this with PyPy, you will see that things get really, really slow when you run it with PyPy. Okay, this is the first one. The next one is list comprehensions. So list comprehensions are pretty nice. And they can be a bit faster. So I can create a new list by writing a list comprehension. So I have an example here. And you do something. Range. So in Python 3, range doesn't create a list, it just has a range object. And now I have my list, which is created here. And this one you can actually write in loop. The alternative would be writing a loop. This would be this alternative and writing a loop. And so list comprehensions can be doing the same thing for x in range, and you write a loop. This is more lines. Times x. Yeah, and it's doing the same thing. I used L again, but you see you get the same result out of it. Yeah, so you can write it this. List comprehensions are often a bit faster. So if you measure this one, so you can actually you can use a time it here. I don't know why I didn't show it. So you can use time it, and time it comes in two flavors here. I use time it for one line in the IPython notebook. Time it, and this is for one line, and this is for one cell. The time it. The time it always is using the Python time it module here, and it measures how long things take. And you see it's a tiny bit faster. So it's not slower for sure. It's not really much faster, but it's can be more useful. If you do something and you want to create the sum of numbers, you could do something like this. You could say sum x times x for x in range something. Let's do it. Let's set an n to something, to 10 for now. And this would be the version that uses let's put a list comprehension first. That's a list comprehension. This would be a list comprehension. And you can achieve the same thing by not using a list comprehension, by the generator expression. By a generator expression by skipping this parentheses. You wouldn't create this intermediate list. Yeah? So this is especially good for memory usage, because here you create an intermediate list. And if the list is getting big, then you might get into problems with memory, at least the use of the memory. And you might also check the time it. Yeah? So you can time the things very quickly. This is always nice in Notebook. It's very little overhead to do the timing, and you can see what is fast. And actually, I don't want to use. I want to use an n here, and you see down there is a little bit fast already. So if I make the n bigger, let's say 1,000 first, and then you run those cells again, and you see how long it takes, if you can gain anything out of it. No, it's not faster actually. For the small one, it should be. Make it bigger. So you can use the memory tools, and you can look at this memory thing. No, it's not faster here. So sometimes it's not intuitive. Yeah, the sorter should be a bit faster because you need to allocate the memory for the list. But obviously that's not faster in this case. Here. Yeah, so, but if you measure the memory, you should see a different thing because he just needs to create the immediate list. Yeah, maybe the other operations take so much time that it doesn't matter here. Good. I have a small script. Now the next one is this local versus global. Yeah. Local ref. Local versus global. So we looked at this already, but now I have it a bit, even look at globals. They have the script that shows you load local versus global, local ref. What is it? Local global. I'm in the wrong directory. So I have to go to the algorithms directory. And now let's look at this two. This can be interesting. Local global. So what I'm doing here, I have a global variable. So global should always be, if you use PyLint, it was asked you to use or uppercase, so it's my global. And here in the loop, I use my global directly. And here I set my global to a local one. We had this before, but we do it for built-in also. And that's what I'm doing now. And now I use the profile and run this and run it for a bigger test and see what's coming out here and what the stats are doing here. So this is the first one. And the second one, I loaded in the meantime, but this thing is running. Load global. Okay, now it's coming out. And see, we have this two functions. One is called repeat, the other one's repeat local. And if you look at the runtime, this is the first one. Repeat takes about 8.7 seconds, and repeat local takes only 7 seconds. So there's a difference. Not gigantic, but there's a difference. Always forget what I have here. Local built-in. Yeah?
So when you look at this list of stuff, how do you know what lines is looking at?
Yeah, you see this one. This is a little bit because it now has a bit. It's just wrapping around. If you have it, you see it in one line. This is a This is the name of the function. This is the name of a function. That's the total time, and this is the name of a function total time. This belongs there. Yeah, it's just because to make it see, I make a font big out of it. If you make it small, then you see it. So if you do this, you see it better. Yeah. 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 You see, now it's nicer to see. If you have it's a nice table because it's difficult to see. You see, and now you see, okay, this is the total time, and then you have here you have the line number and you have the name of the function, and then you can find it. But if you make it big, it just wraps around. That's why it looks so messy. Yeah. But I make it bigger so you can see something. So it is always, yeah. Okay. Maybe I made it too big. So now I do the same thing, but now I use a built-in. You see, true. It's a built-in here, and then but it's still doing this lookup. It looks in the local first, and looks at built-in actually, and then it goes to the built-in. It looks at global, and then it built-in. It's another lookup, and now I set, I don't know if you want to do this, but I set this my lowercase true to true. And I'll do the same thing again and do the profiling and see how long it takes, if there's a different thing. But this might be something, if you have a lot of inner loops and a lot of these lookups, it's very easy to do, and it doesn't hurt readability. Yeah, it doesn't hurt readability if you just have this one line. You say, okay, my local name now is this other name, and I use it in the loop a lot. If you use it only once, it makes sense because assignment takes all the time. You don't gain anything. But if you use it a million times, then you might think about it, and you see now here, I go down. Oh, the difference is less, from 7.2 to 6.6. Yeah, there are some. You see a difference. It's not. Actually, is this the right one? Yeah, actually, it should be repeated. Yeah. If you do this in Python 2, because it's changed in Python 2 and Python 3 from that true became a keyword, and I'm not sure if this has any impact on this one. So now I'm running the whole thing with Python 2. This should work because. Yeah, so as long as you have Python 2 installed and you can call from the command line with Python 2, then you can use it as a magic command here. You don't have to switch back and forth. And now you see a bigger difference. Yeah? So 6.6 versus 4.6, so it's 2 seconds difference. Yeah, because true became it's a reserved word in Python 3, not in Python 2. So there might be some changes on this one. I might use a different built-in, like sum or something like this. Okay, that's some small things you can do, some small algorithmic things you can do. And the next algorithmic things, how much time do you have? Yeah, not so much, fortunately. The right data structure. This is a big thing, actually, if you use the right data structure, because the data structure is not only how you put the data in, it's also the algorithm behind it. So Python comes with lists and dictionaries, very mighty data structures, and they have algorithms behind it. Especially dictionaries, they have this hash table, and they give you a lot of things for free. So from time to time, I still had to program in Fortran a little bit, and I really miss dictionaries in Fortran. And I haven't found anything that's any implementations of a dictionary. I have maybe there's some commercial library, but I couldn't find it. And that makes a lot of things much more difficult. If you have a problem that's 2 lines with dictionary, you write pages and pages of Fortran to do something, and it's still cumbersome. And might be slower. Also, if you're not really versed in all those things, you have to put a lot of effort in there. So dictionaries are very, very good, and they can help you. But there are other data structures, and I have a few things here, different things what you can use for different purposes. Nothing is free. So if you use a different data structure, it might be faster, but might have disadvantages. So most of the time it has advantages one side and disadvantages the other side. Depends if this matters for you. So you can use built-in data structures, lists versus sets, we look at this, but also there are some data structures that come with Python, some library which I focus on. If you get deeper in, you can find also other data structures in external libraries. And using the right data structures can make a big difference depending on your needs. Yeah. For instance, if you do this the lookup in a list in a dictionary. So let's go to data structures. Data structures. So if you have questions, always ask questions here. So the problem is obviously I have quite a bit of material and we only have half an hour, and I would like to cover this. That's why I skip the exercises. Otherwise, I really like to do exercises because you need to do something yourself, and it's typically a bit more interactive. But otherwise, you wouldn't cover this thing here. Data structures. And if you have questions, please always ask questions. That's always good. Then I can see what you're interested in. So a few things, like if you have a list, list range, so make it n. Yeah, if you have a list of size n, and then in this list you put some kind of a target. I'm looking for some kind of a target. And I put this target in the middle, so I use this just as example, n divided by 2. This is integer division, yeah, so because in Python 2 it wouldn't work if it just divided by 2. In Python 3 and Python 2 it still would work, but it's still recommended, works there. And I just say this is my target. And then I have my set S, which is just a set of list. So, and now if I have this set up, I can use time it and time how long it takes to look for my target in my list. And then I can use the same time it to check my target in my set, in, to write in if you mean in. And then you see here, takes a bit. So this time it always does 3 runs. If I don't, you can specify how many, but 3 runs, and every run takes about 1 second. If things take longer, so if one function call takes 10 seconds, it takes 10 seconds. But typically it's more or less 1 second. And you see here I have 1.5 microseconds, and here I have an order of magnitude faster, that's nanoseconds. Now it's 10 times faster already. Yeah?
But Tom is also pointing out, I think, one run in
Yeah.
particular that was
Yeah.
an outlier.
Yeah,
But that's
yeah.
the growing process
Yeah.
of growing the actual set.
Yeah,
Right?
yeah. So time it is also, I think, especially people from PyPy, they don't like time it because time it measures time, influence your system. Actually, it turns off the garbage collectors for I don't know. So it might, yeah, because it just checks what's the fastest algorithm. There are a few things that time it maybe changes the measurement in a direction you don't want. That's why you might want to do it yourself. You can achieve the same thing with writing it yourself using the module time it. And you should always have this import time it. And it's a module. So the name is the same, not by coincidence, because this % time it uses the module time it behind the scenes. But this one time it also has what's called a default timer, which you should always use. Default timer. And when you default time, you get a timestamp. So this timestamp is, as I said, is depending on your operating system. So when you use Windows, you might get a different absolute number, but it doesn't matter. What matters is you want to have a difference. So you have a start. Yeah. So you can say there's a start timestamp. Then you do something. Yeah. You do something, and then you get an end timestamp, which is actually the same thing minus start. It's just you want. You don't have to. You can do it in one calculation, but just minus start, and then you have a duration which is put end minus start. No. This is duration already, sorry. Duration, sorry, just stupid. Mix them up, duration. Yeah, so this would be the duration, and then you can look at the duration, and that's how long it takes. Of course, this is a little bit, because 1 + 1 is very fast. Yeah, so this is off. The overhead of my measurement is much too big for this short, typically. So that's a little bit difficult, this measurement, how to do this. You would need to repeat it many times.
I don't want to get too far off the actual topic, but the point I was going in your previous steps with the time at measurement that you're doing, each run is not independent then?
Yeah, because it's cache. It has caching effects and other things going on. Typically, if you do the same operation, depends also the size of the data or whatever you do. If the computer can keep things in the cache, loading data from caches from memory into cache can be very expensive. And this will be in here also. But this is something, if it's in cache already, then you can be lucky, that's fast. If not, and this can be easy in order of magnitude, or here see 2 orders of magnitude.
So in this example where you have two synthetic time-its, if your time-it simply were to be uncached and run once, depending upon your actual implementation.
Yeah, but if you rerun it, you might get rid of it because it keeps in cache now. So this is it's still. But if I rerun it directly after it may be.
But if you were to run both time-its for one iteration each,
yeah.
the delta
Yes, you can do this. Yeah. But see,
magnitudes that we're seeing here.
it's a factor 180 is a factor 15. So if you repeat it, you get a different there's effects there, and that's difficult. Yeah. So that's why it's typically doing it 3 times and takes so fast. This is just one approach.
Sure.
The thing is, the question is right or wrong. At least it's comparable, it's reproducible. Do you take the fastest one? It might still be wrong. Yeah, you can also average it out if you wanted. It would be other approach. So if you use your own timing, so no, you would write a loop. So how many times you want to repeat it, but then the loop itself adds overhead. Then you can measure how long the loop would take and subtract the time of the loop, of the empty loop as a pass. But the pass also takes over. So there's no easy solution. But if you want to do what I'm up for, this order of magnitude comparison. Now, if I increment my n here, my n, make it much bigger. Just make it really big. Yeah, 1 million. So, and now you will see we had about 0.1 millisecond, or about 100 nanoseconds for the set, and you will see the time for the set stays the same. So this is time complexity. I'm going to look at it. So, yeah, it doesn't matter how big the set is. The lookup in the set takes about the same amount of time. The same works for a dictionary, actually. Well, dictionary, but you don't need a dictionary. But dictionary takes way more space because it has key values. You only have keys, so to speak. But the time for a list, more or less, if you assume it's somewhere in the middle, which is statistically right. Of course, if it's the first thing you're looking for and you always find the first one, the list is faster because you just do one comparison and you're done. But if in the middle, then this is faster. So it might be worthwhile to convert your list to a set for a lookup. If you look it up only once, it doesn't make sense because converting the set to a list also costs time. If you go through the whole list, all the time you save, you use up for converting the list to a set. So, but if you need to look it up 1,000 times for some reason or some different numbers, then it might make sense to convert the list to a set. That's a simple thing you can do. And typically, when a set is okay and I want to I use even though it's just 5 elements. It doesn't speed up if it's 5 elements. That's not fast at all. But I express that actually a set would be a good thing. That sometimes I like to do this. And for some reason it might grow to 5,000 or to 5 million. Then you have a set already. Yeah? It's just as long as everything's small, it doesn't really matter too much. If it's a list or a set or whatever, you won't see a big difference because the call overhead it's much bigger than what you get there. But if you might have a chance things get bigger, then you can use it. If you use a list or set, it doesn't make your code more unreadable in any way. It might be even clearer. They say, okay, it's just for a lookup. I just create a set for lookup. Yeah, this is something. So you always have to say, what's the price I have to pay if I use a list or a set? Yeah, there's no big difference for this case. That's when I can use a set. It doesn't cost me anything extra. Okay, there's something here. I have some examples here. Let's go through. Yeah, let's just keep going here with the set. Yeah. I skip this a little bit. This is too big. The other thing is, there's some, now I want to go, that's a built-in. So you can list dictionary sets is this thing. The next one would be a DAG. So there are a bunch of built-in data structures in Python that might be useful for your purpose. It might be faster. So let's go to an example here, which actually uses a DAG. Are you familiar with a DAG? It's a double-ended queue. So as I said, Python lists are very good to append at the end. That's what they're designed for. If you want to append or prepend at the other side, they're very bad. Because every time you do this, you need to copy the whole list. And this DAG, a double-ended queue, actually allows you to do this. And you can do this here, and you can work with this. So let's have this. This DAG. Yeah. So just have this. As an example of what it's doing, and then this would be one way. So this is quite long here. Just shorten this a little bit. So you say from collections. So the collections module offers a few of those interesting data structures, and one of them is this. Why doesn't it work? Yeah, import. Sorry. Yeah, that's why it doesn't work. Import. So I import this deck, and the deck is as follows. You can create a deck from a list, for instance. Deck, and you can throw in a list, for instance. Something like this, or range would also work. And now you have this deck, and the deck offers you a few operations. You can append, and you can also append append left. So that's a different thing. You can append and append left. That's something you cannot do with a list. So appending is clear. So if you append something, then you have this new number at the end, and my deck now has this. But also you have append left, and you can append something to the left, and you have this append left. And this is efficient, so you can do this append left, and you can do something when you do an insert 0. If you have a list, then this is very expensive. If you want to append left, you would say insert 0 minus 1, let us say. Yeah. So, and this actually requires you to copy the whole list. The same thing goes when you delete something. When you delete something, because the list, everything is in memory. If you delete something, then you use up a lot of time here to do something. Therefore, it might be better for this kind of structure to use a stack if you want to do something like this. I have an example here, so you can also use rotate. If I say rotate, then because the thing is with a deck, you can only add and also pop and pop left, as remove, only from the ends. You can never go in the middle. So if you want to remove something in the middle, you have to rotate. So if I rotate by 2, then my deck now is rotated, and I have moved everything by 2, just going around. Yeah, going around. And now I can do an append or a pop left or right, and then can potentially rotate things back. This would be a way of doing this. So instead of removing something from a list, for instance, you can rotate from the middle of the list, rotate your deck, do a pop, and rotate it back, for instance. That's something you can do. No, it rotates by 2. So my original deck looked like this, yeah, like this, and now everything is moved by 2. So the last 2 are moved to the end. If I say -2, then I move it back again. So rotate -2, then I can move it back. And now I have my original one. Yeah, that's what we can do here. So you can rotate things back and forth, and therefore you can do something. And I have this this example here. This example function that you want to remove something from your list. Let's do this quickly. Let's do this function and see how long it takes. So I check. I have this function, so I don't want to reinvent it. I have it somewhere. Yeah. Here. So I have 2 functions. The first one is remove from list. And the second one is this with the deck. Now here there's an example. You have to write more code, but it's getting faster. Remove list. So I give it a list. I have my list. I put in here, and I say I would like to move between start and end. This is the first one. Yeah. I give it my list, and then I say actually my list, and I do just this assignment and say start end equals an empty list. So that's actually deleting. Yeah. So you can assign a sublist to a range on the left-hand side, and that's essentially deleting everything, start inclusive, end exclusive. That's what I'm doing here. That's my first implementation. Now I have a second implementation. It's a good example. You make things more complex. Now I have the same one. Remove from deck. Remove deck, and this should be underscore. So remove deck, and now I give in my deck, and then I also say start end. So the interface is the same, but I have to do a few more steps. So now I introduce complex. The list implementation was one line. This one is a few more lines. So I say my deck, and it should be underscore. My deck rotate. Rotate. So I rotate to minus end. So I cannot even program it out of my head and have to look it up because it's not that intuitive. Then I say for counter in range. So range is fine here. So as you know, in Python 2, you should use X range or replace it. Typically, if it's getting bigger, it's recommended. And minus start. So I have to go so many steps, and I can use this deck pop. So pop is like a list pop, just removes the last one at the end. So I would remove so many elements as I want to remove, the difference between end and start, and then I have to rotate it back. So my one-liner became now a four-liner. Yeah, just 4 lines, the implementation of the function is 4 lines. And now I can move the same thing back. I have to say rotate, and I rotate by start. So let's have a look. If I have my list, if I say, just to see if it works at all, remove list. And I put in my list, and I say I want to remove 3 to 6. So I have my list, and the list went from -1 to 9. So I have to now make a deck with the same number. So a deck is a deck range -1 to 10, -1. So it have the same numbers. So the deck looks like this. And then let's look at my remove deck with a D, producing the same result. And I have to specify 3 and 6, of course. And then, yeah, looks the same, so it has the same result. So now the thing is, I want to check how long it takes. And for this, of course, I need to create a list and a deck, and then do my time it measurement. Yeah, and you can do this measurement. And if I have my list, something like this, let's say 100,000. And my deck is also, I just convert this one. Yeah, and now I can say time it remove list, and I want to have my L, and I want to remove 3 to 6. And I do the same thing. Time it. I do the same thing with my deck, and then I see my deck 3 to 6. Oops. Why doesn't it work? It's empty. Do I need to copy this? Yeah. No? Now I made a copy. Why didn't? It's empty. Why is it empty? So never do a live demo. What's wrong? Why is it empty? Isn't it? Yeah, it's empty. Obviously, it's empty. Can I just make a deck from a list? That's something strange. Yeah.
Each iteration is modifying it.
Don't I assign it here? Yeah, it's so strange. Ah, yeah. See, the time it. Ah, yeah. Right. Thank you. So I cannot use this things. I can use it only once. So because I move the stuff again and again. Of course, it doesn't work. So if I do one repeat and one, then you have this the difference. See, now I'm about 10 times faster if I do this, if I remove only 3 elements. The problem is if I remove more elements, so I need to recreate this here again and again, because I'm modifying it. So measuring time for modification of the structures is kind of difficult. As you see, I would need to recreate it, and it would take off the time I need to recreate, but it would be measured in here. But if I make it bigger, so if I have 60 here, so I type in the numbers, you should have actually said it. You see now the time difference is getting smaller, and if I recreate it and now I run it with 600, so I delete more and more, then I'm getting slower. So using your stack can be faster. I get an order of magnitude speed up, which is pretty good, isn't it? If I just delete a few. If I have to delete a lot of them, then the overhead, you see what I'm doing, I have to do all this rotation. So for each of them, I have to use a pop. So you have a lot of this method calls. And method calls are pretty expensive in Python. So I have 600 or so method calls now, and this will add up. So it's not always clear. So if you test it and it's faster, you need to test it for a variety of sizes of your data structure. That's very important. Because if you use a small data structure, you might have a different result than a big one. You have to have the input of your tests, how fast you have, just to cover pretty much the range you expect. Otherwise, you might have some strange results. Yeah? You cannot say it's faster here. This is just an example, so you can play around. It doesn't take too long. This one makes your code more complex. You might gain something if start and end is very close. If they're far away, you make it slower. Yeah? This is one lesson here you can learn. You can play around with it. Okay, this is something we have here. The next one is default dict. This doesn't help you to speed up how much I have it here, so I put it in. But it's another data structure. It's more convenience than speed. From collections, do you know default dict? So default dict can be interesting. Import default dict, and this default dict can be you can give it a, for instance, you say my integer dict, and you say default dict, and you can provide it with a function or something callable. So actually int is not a function, it's a class, but if you can call it like a function, it's callable, it doesn't really matter. And now you have this one, and you have I shouldn't use ID. idict. So it's not a good idea to use built-in names. Idict, and now I have my idict, and this is just, if you look at this, it's in default dict, it's in empty, but you can use it as in normal dictionary if you would do something like this. A plus equals 10, for instance. It would give you an error message, but if you access a key that doesn't exist, it calls the int method, gives you an int. If you call int, you get a 0. So you can write your own function actually. And this is pretty common, which replaces you might set default. So you have this, and this can be a little bit faster than using set default from time to time. Depends what you're doing, your algorithm. It's more convenient though. It's an extra import, but instead of using set default, which would do, set default wouldn't work with an integer, but would work with a list. So you can make a dictionary. Yeah, you can make a dictionary, and then you can say d set default, and then you can have a key, and then you can have an empty list, and then you can append to this list. Yeah, and this would work. So you don't have to check first if key is there. If it's not there, add the empty list. Otherwise, append to list. So you can use set default. But it doesn't work with the integer. Yeah, because you cannot modify an integer. When you give it back an integer, you can list is you can change it, and then you can append to it. But you can achieve the same thing with if you have a list dict and you use a default dict, you have the default dict, and you can put in default. It has a big zoom, that's why it's jumping around all the time. And now I have a list as a function, and then you can use my ldict, and I can use append directly. Addict A, and I can use append directly. Something like this. Yeah, this would make it easier. And if you use it in some cases, it's a bit faster. It's not much faster. Now my ldict also would look like this. It's a dictionary in there. And this is default dict, can be useful. And I have some examples here of speeding things up and how fast things are. And it can be a bit faster, but it's not much. It's just a factor of something. Don't know where the timings are. Yeah, it's like 70% of the time, so it's not so much faster. Okay, we only have a few minutes. I want to go through the rest of this material, and So we covered all the things which I think is important. The caching thing, we just actually quickly go to this big O notation. Are you all familiar with big O notation? So big O notation, this is important for the algorithms. So it describes how long it takes for an algorithm to run compared to the size. And the nicest thing is O1. O1 means it's independent of the size. And Python examples are what we just did. If you look at length of a list, length of a dictionary, if you index a list, if you delete something in the list, if you do the X in dictionary X and set, that's what we just did. It doesn't matter if it's 10 or 10 million, it takes about the same amount of time. Not exactly. And the list append is also independent. It doesn't matter how long the list is, append takes the same amount of time. Linear is okay, which when your data structure gets 10 times as big, it takes about 10 times as long, more or less. And this would be loops. And everything when you loop over these elements. O(n) log n, which is a bit slower than linear, would be, for instance, sorting. So Python has a pretty fast sorting algorithm, so sorting is there. And then everything else quadratic would be have a nested list. So you want to avoid those, these nested structures, those quadratic ones, or even higher ones, and try to flatten it. It's not always possible, maybe, but this is something you need to be aware of. And actually, using the set instead of list is using O1 versus O(n) for our lookup. Yeah? Lookup in a list takes O(n) typically, more or less. If you can be, the worst thing is not a list, you have to go to the whole list. Yeah? Therefore, they have this. So when we have some of these, so I have this helper profile speed here, and I just go through because we don't have much time. But it's just an examples when you do something like if you have this list, and you go through, and I do this insert 0, which is an anti-pattern. So I do insert 0 and grow my list by always appending to the left-hand side. And then I do the same thing by just appending to the right-hand side as it's supposed to be. And then I compare these, and I run these, with my functions and see I run it with different sizes. This is just run here with 10, 100, and so on. You see if it's the size is 10, this append is 1.6 times faster. But then when you increase the size, if you go to 1,000,000 to 2,000 times faster, that's 4 orders of magnitude difference. So it's a big, big anti-pattern. Yeah? And this is depends because how you do work with. We have to every time copy the whole list around because you have to recreate them in memory, and that takes a lot of time. Yeah, factor 2,000, it's quite big. But it is, if you see, and if you have 10 to the power of 7, it would be an order of magnitude more, typically. So that's something you can keep in mind. Yeah? So you can also just reverse it, and then you do the reverse. Then you have to measure the reverse and have a few of these extra things. Yeah. Good. This is, I only have 10 minutes. This is some short thing about algorithms. So algorithms is the one we get potentially, if you find the right algorithm, you find the right data structure, you can get many orders of magnitude speed up. If you use other methods, rewriting in C or using other methods, typically you won't get so many orders of magnitude. So if you really have lists of lists and you use NumPy or C, you can get a factor of 10 up to a factor of 100, maybe faster. That's possible. But then that's it. Typically you won't get much there. If you use a different algorithm, you can get a factor of 10,000, 100,000 faster if you find a good solution. Okay, one strategy I'm here is caching. Caching means you want to avoid recalculation of the same thing. Caching typically only works if you have something that's deterministic. So if you have a function and you put A and B in a function, you get C back, and it's always, if A and B have some special values, you always get the same C back. This would be pretty much a deterministic function. If you have this kind of function, then you use caching. You don't need to recalculate the same thing. And this is, again, the strategy. For caching, you need memory, so you use memory for speed. And for some applications, this works. A lot of web servers work with caching, so if you retrieves the same web page all the time and hasn't changed, it can keep in the cache instead of being recreated all the time. Yeah, and they have some of these examples caching, and again, you just need to apply. If you can run, you can use caches. There's a LRU cache in Python 3, backported to Python 2. This is the least recently used cache that's recommended to use, but you can also create your own. It's not that difficult, and sometimes it might make sense to create your own, or at least to learn something. If you use it in the end, it's a different thing, but you learn something how things go. And that's what I have here. To create a cache, you need to identify the arguments, and there are different ways. You have this make key function here, which gets a function and gets the arguments and the keyword arguments, and produces a unique key, and I just use the string. And what I'm doing here, I take the function, every function has a module and a name, and that's what I'm doing here. I just create strings out of these positional functions, and then strings in this format out of this one function. You get this string. So it has a function name in there, the module name, the function name, and then all these arguments. If you do this, yeah, if you run this, and then you can have different functions, just one of them. And then the simplest cache would be just a dictionary, and you just store everything in the dictionary. The key would be the key you just produce for this function, and then I have the result in there. And it would be a very simple one. And this, again, this is a very nice application for a decorator. So you have this decorator, and this decorator I provide like this. I have this get key method, which I throw in from, I just imported here, and I have the cache, which is a dictionary. You can supply your own dictionary if you like. And this is a 3-level decorator because it takes parameters, so you have parameterized ones. So you have the outer function, the inner function. This one takes the parameters for the decorator. This one actually takes a function, and this one is a function that will replace the original function. So a lot of functions here. And this one has a function to wraps, and then this is pretty easy. It's just here doing the thing is just get the key and goes to the cache and retrieves the value from this dictionary. That's it. If this doesn't work, you get a key error, and then you have to recalculate things. So it assumes that most of the time that maybe there's one miss, and then you have 100 or 1,000 times where things come out. Then it's really useful to do it. If you have one miss, and depends very much how expensive this function is. If this function you're using here, you want to cache, is just 1 plus 1, it doesn't make any sense, because the overhead to calculate the key is much bigger than the 1 plus 1. If this function is working with a million numbers or doing something expensive with files or whatever, then it might be useful, but you have to test this out. So caching can be more expensive than not caching if the operation is cheap. But if the operation is expensive compared to whatever, then you can do this. Yeah, and then you have to do the return game. And then the usage is easy, just apply the cache, and I have my add function here in my cache, and then it returns this one, and you will see, I put a sleep in here to see how long it takes, and you don't see the time now. The next time it will be much faster because it just retrieves it. So this sleep just mimics it takes something very long. Typically for A plus B, you don't need to cache. It would be much more overhead to have the cache. So you can roll your own. If you want to make it more sophisticated, it will be much more effort. Therefore, you can use built-in caches. So if you go to the Python collections module, you have the least recently used cache, which is pretty useful. That you can specify how big it is, and then you have this one. So then have a non-deterministic cache, because now everything in the cache will stay there forever. And here you have a different one. You can you have an age. So there's one way, so it just goes by how long it's going to stay. So this one only has a half-life of, or has a life of a few seconds or minutes or hours or whatever, how long your program is running. And after a while, so web pages typically have this expired thing. So if a web page, of course, it will be cached in different places. Even your browser's caching things, and only if you reforce it then or something, and then there's a time. And this is just one strategy. Just a simple, just gives you the principle. So it's typically not really. There are much better implementations, but gives you an example. And then the only thing is now you store two things. You store the result and you store the age by calling time. Time here is fine because it's not so fine-grained. You don't have to use anything else. Time gives you a timestamp. And here the key is it's a compound key. It's a tuple of the last time and this key you calculate from the arguments, from the same arguments. Yeah. And then you just say you have this deprecate, you have this notion of deprecating, and when you retrieve the key, it's a tuple, and you do tuple unpacking here, so the value, the age value, and the value itself. Yeah, value age and the value itself. And then deprecated is the case if the age is not 0. So if the age is 0, it will never be deprecated here. And the age, the value, the current value age plus age is less than the current time. And the age you get out, where's the age coming from? Yeah, the age is of this one you get from here. To check myself, it comes from up here. So I supply the age here as argument for the decorator. Yeah? So if this, and you get a timestamp, and if it's older than a day or older than an hour or older than a second or whatever, then you would recreate it. That's very easy. Yes, this deprecation. That's something you can do with memorizing, which is called, and then you can do this, and then if it's too long, you have to run the example actively, then it will go. So least recently used cache, so you can have this, I mentioned this. This is pretty useful because this doesn't go by time. So if you say, okay, I can size this cache, it has 100 elements, and it will store up to 100 elements, and as soon as the 101st one comes into the cache, it will throw out the one that has been used the least. Yeah? So if this one has been used 10 times, this 10 times is only once, this one with the ones has to go out. And this is pretty useful. And then this is used a lot because you get the most effect for the things that get reused the most, typically. It's the same function. And you can, it's inclusive in Python 3, so starting with 3.2. And if you have 2.6 or higher, which you always have, then you can import it. Yeah, you just pip install backports functools LOU cache. It's in functools, not collections. And then you just have a decorator. So in a decorator, and you can size it here. I use a max size of 2 in this case. And then if anything bigger than 2, it will throw it out. You see this. You should put a print in, actually. So just run it. So if it's 2, it will rerun it. When you have a cache info, you can look inside the cache, and you see how many hits, how many misses, the max size, the current size, and you can also clear the cache. So you can remove it. Yeah, clear is just like dictionary clear. It just removes everything. And there's even software called memcache. Memcache is software used quite a bit for caching of web pages. It uses the same principle, and this is a pretty high-performance thing for storing static input information, for instance. Okay, the time is up, but I'm on the last page. And I have a small compilation of tools. There are a lot of tools. We just dipped into the first thing. I think it's just more to get your appetite on this. So the first you have to understand what's going on, and you measure, quantify, and then you can decide if you want to use a strategy. So if you can go for the algorithm, go for the algorithm. Look for it if you can find something. If not, you have a lot of tools at your hand in Python. There's way more than I have here, but a few of them. So NumPy would be for numerical things the first thing to do. And you might use NumPy even before you use lists at all, because NumPy might make your code much shorter than using loops over lists. So that's the thing. You can use PyPy. So if everything is just pure Python, you have a few extensions. So PyPy cannot work with all C extensions. You can work with some of them, some are compatible. But if you work a lot with pure Python, then just trying PyPy it doesn't cost you anything. You just need installing, you say PyPy instead of Python and run it. And on average, on the Python benchmark, they have 6.5 times faster. So it's likely that things get faster. Not everything gets a lot faster. There might be a few things that get even slower. There might be exceptions, but many things get faster. Cython, so as I mentioned, in our course we have Cython, which is a combination of Python and C. So you can convert Python step by step to C just by using some type declarations. And you can also use existing C extensions pretty easily with Cython. C types is similar in terms of, no, it's a bit different. You can use DLLs or shared libraries, and you can include them. They have nothing to do with Python, you can call them. CFFI is a new tool, comes from the PyPy project, and is similar to, but works with normal Python, and you can also easily write C extensions. That's a very nice tool. Number is one that compiles the code to LLVM, which is a low-level virtual machine. So there's also some decorators, just very simple, just put a few decorators, and maybe things get much faster. Depends. It's not for everything, it's just a subset of Python, but it can be nice. F2Py, I use F2Py to wrap existing Fortran, so if you include Fortran, F2Py is very nice, gives you a lot of things. You can write a C extension by hand, not recommended. Used to be the way when I started Python I did this, but it's a lot of work and not very maintainable. Then a lot of tools that wrap C extensions, Swig, Boost, Zip, that can be used. PyInline, I'm not sure how far this is going. Theano is a very high mathematical and works with GPUs. If you do a lot of math, you might look on this one. Then there's also lower level GPU programming, PyCuda, PyOpenCL. It's not for everybody. Copperhead is a higher level functional thing for things. You can use some middleware things. Weave is still part of SciPy. PyEuphora is a new one I just heard about, which also gives you a parallel Python. So they have a context manager with, and then from there on, you can only use immutable data structures, and they can run in parallel. And they scale to 1,000, of course, what they claim, for certain types of tasks. So all these tools are not perfect. They don't work for everything. You have to find the right tool for your right purpose. And there's no general. We always have to some criteria. What do you want? What kind of problem you have? And then the thing is you have to try. You have to try things out. Good. Last page. That's it. We made it through. 75 pages for 3 hours. Typically, it's 1 day, so I do it 1 day with exercises. It's a bit condensed, so you're now supposed to do the exercises yourself, which you don't, but if you're interested, do the exercise and try it a little bit. I hope you got something out of it, you get some understanding. It's a bigger topic, and the tutorial can just be an introduction. But you know there are some tools out there, you can use the tools, you can apply them, and you can adapt them. And have a few scripts, maybe they're useful as a starting point for your own endeavor. So, thank you very much. You are hungry now. Have lunch. If you have questions, ask questions. Please go to the survey. I gave you the link. This should be okay, hopefully. I didn't mess up this link. Go to the link for the survey and just give feedback, because the organizers would like to feedback how this tutorial went. Thank you very much.